Welcome everyone. We're still waiting on a couple of presenters for our first session, but we've almost got our first block. I think I'll get going with the introduction so we don't fall behind, but hopefully we'll have a few folks joining us as we go. So welcome to our session, Antarctica and its neighbours in supercontinental cycles. I'm Jacqueline Halpin. I'm a geologist at the University of Tasmania in Australia, and I'm joining you from Lutruwita, Tasmania, and so I acknowledge the Palawa people as the traditional owners and custodians of this land that I'm joining you from. I'd also like to introduce co-conveners. Laura Morrissey is online, and Nathan Daczko, who'll be helping out this session, and also our colleague Geoffrey Grantham, who hopefully is joining us for the next session. So we've got two back-to-back sessions, each 2 hours. In this first session, we've got two groups of 4 speakers. So we'll have 4 speakers, each giving a 10-minute talk. And then we'll have a 5-minute Q&A session where those speakers will be here together to answer questions. So I invite you to put your questions into the chat as you think of them, but we won't have questions after each talk. We'll just keep them to that Q&A session, please, just so because we were moving between computers and presenters. And we also have 19 posters in the session, so I encourage you to go and have a look. They're all live at the moment. There's opportunity to post comments and interact with the authors there. So Laura will be keeping our time in this first session, and at 10 minutes she will raise her hand. That means that you've made it to 10 minutes, and we ask you to wrap up at that point. I know it's not a lot of time, but we'll try and wrap up at that point. And if things are going on a little bit too long, she will turn her camera on and start interrupting and really asking you to wrap up. And Nathan will lead our Q&A in this session. And then we'll come back for the second session, and I understand that's on a separate Zoom link for that second session, which runs the second 2-hour block. So I'm just looking at our panelists now. We're still waiting on 2, I think, to come through for this first component.
Well, Jackie, I'll keep an eye on that, and when they arrive, I can.
Okay. So we're missing Jeremy, Alexander, and Sawal, I think, at this point. But I'd like to introduce Alan Aitken, who's our first speaker, and I think we can kick off with Alan. Thanks, Alan. Would you like to share your screen?
Sure. Hopefully that looks good to all of you, because it looks pretty good to me.
Yeah, that's perfect. Thank you.
So yeah, thanks, Jackie and Nathan and Laura. I'm going to give this talk on sedimentary basins of East Antarctica, but I'd like to recognise before I start not just the fairly large author team you see on here with their institutions, but the incredibly large community effort over the years to collect data, to run models, to generate information on Antarctica, because we really are standing on a huge pile of information that we've tried to make some sense of. And without that information, we wouldn't have a talk to give or a paper to write. So just a shout out to the entire community who have put in a lot of work to get us to this point. There we are. So the fundamental question that we came in here was, why do we actually want to know more about Antarctica's sedimentary basins? I mean, as most of you here are sort of geologists of one flavor or another, so we have an inherent interest. But in terms of applications, what are the reasons that are going to support a better knowledge? And really, we have sort of important linkages with sedimentary basins at the base of the ice sheet, with understanding crust rate change and past evolution, understanding the sort of the global tectonic systems that feed into that, and then feeding that forward into understandings of how ice sheets work, geothermal heat flux, the rheology of the lithosphere, the history of the lithosphere, groundwater, and interactions between the interior continent and the margins. So it really is, I think, a fundamental thing that we want to understand to put the geology of Antarctica forwards. So just a little bit of review as to what we can do. Obviously, the conventional approaches to understand sedimentary basins are a little challenging in Antarctica. We can do, of course, seismic work, but at the moment that's relatively limited in its extent and scope in the onshore realm, certainly. Outcrop is very limited and very much biased towards certain suites of rocks. So we really are working on the basis of a geophysical exercise to try and understand which aspects that we can detect geophysically are representative of sedimentary basin fill. And just some sort of findings from some recent work here. We can sort of understand with, you see this chart on the right, this is showing some of the data sets that are more useful in discriminating sedimentary basins from igneous and metamorphic rocks in a rough order of ability. Now there's data sets that are much better than that, but they're not available continent-wide. So the focus of today's talk really is on East Antarctica. And I think one of the sort of concepts that's quite persistent is East Antarctica start off as a basement-dominated cratonic region, which is not untrue, but at the same time, I think we forget in the same time step to sort of understand, well, what are the basin forming processes that are going on? Where are the basins forming? And why do we have the basins where we do? And that's really going to drive us forward in a conceptual understanding of the importance of sedimentary basins for all those applications that I pointed out just before. And, realistically, we have a very long history of understanding basins here, like the Wilkes and Aurora basins. We go back to 1972, the first sort of definition of those as major sedimentary basin systems. And, over the years, we've developed a really kind of a diversity of understanding of many of the smaller basins, as well as understanding more about the Wilkes and Aurora systems. Coverage does remain quite scarce in a lot of areas, particularly of the really good data sets that we want to really pin down. Basin history, for example, is not easy to get at. But there is quite a lot of information there. There's 50 years of research. And there's what we're focusing right now, the group that was sort of listed at the start of this presentation, was really building that synthesis together of what is known at the moment, developing the knowledge of the systems, and making that a public resource that can be updated, edited, and used. And not just used by humans, but used by machines. So it needs to be digitally accessible. It needs to be quite systematic in its structure and all the rest of that. So that's the real driver of what we're trying to do in this work. But I've got sort of a first go through for some of the major elements of East Antarctic sedimentary basins. So the first element, sorry, let's move my camera. The first element is, the first phase is really sort of pre-Gondwana or assembling Gondwana phase into the Ediacaran era. And you've got this coherent East Antarctica forming. We know we have the East African origin or East African Antarctic origin and the Kunga origin, and we've got the developing Ross origin in, well, I'll call it the West. It's actually, let me get the pointer up, here. We don't maybe know with much certainty that the locations of all of the sutures and tectonic elements during this period within Antarctica. I mean, there's numerous maps, numerous theories out there, but they don't all, I don't think there's quite a consensus on those yet. But we basically have potentially basins forming on the Craton, or at least what's now the Craton, potentially in areas like Johnny Maudland, these green basins here, seem to be relatively old basins that are aligned with late Pan-African structures. So these could potentially be, associated with the Gondwana forming period. We've got basins like the Sandow group down here. I forget the exact date of that, but that's definitely Neoproterozoic. There's a major basin here along the Vostok Highlands. So, that's proposed to be a passive margin that's brought into a collisional zone of a certain age, it must be confessed. And we've got sort of major deposition happening potentially in the ASB region more broadly, which is potentially equivalent to, or in some form equivalent to Centralian superbasin type rocks. We also have along the margin here, we've got Barrow group, Beardmore group, and various metamorphosed equivalents along here that are representing the edge of the craton adjacent to the ocean, but also sort of stuff offshore here on island arcs and so on. The next phase is really a bit of a changed system. We start to develop the Ross orogeny quite strongly, and we start to see more basins forming in this region here. I've included the Swanson formation here, also Ellsworth, Whitmore, because these, of course, were close to the margin at this time. But then we also have rocks like the Bowers and the Robertson Bay group that were forming off the margin at this time. So there's been a little bit of tectonic dislocation. That's why I don't have an actual tectonic map of where these were. But there's definitely this sort of evolving situation from a pre-orogenic through synorogenic to post-orogenic rocks associated with the Ross orogeny. And then we get into the big sort of on-craton phase, and probably the most impressive basin of them all is the Beacon supergroup basin, or the lower Beacon supergroup is sort of where it begins. And the mapping that we have, I mean, we've got the exposures all along the Transantarctic Mountains here, but the mapping that we have identifies these broad basins in the hinterland, Wilkes subglacial basin, but also at South Pole, Pensacola Pole, and inland of the recovery area. And these are very consistently sort of, they've got the same morphology, the same sort of look about them in the data sets. And they're all this nice little, defines this sort of continent scale strip here that is there. And the model that we're looking at for this one, which is not new to our work, but is basically a retro arc foreland setting to platform setting. But it does show in the details, we've got quite a lot of along strike segmentation into depicenters that vary in thickness and vary in width along strike associated with sort of these major sort of David Glacier, Scott Glacier, Beardmore, you know, the big glaciers on here are actually delineating different depicenters along this margin. So for those of you who don't maybe believe the retroarc foreland interpretation, I just include a little picture of the North American example here. So it's about the right width, it's about the right distance back from where we have the magmatic arc rocks. And I think that makes it sort of clear that the Beacon supergroup is not just along the Transantarctic Mountains, and that system extended a lot further inland during its formation. And that really what we see on the Transantarctic Mountains is a consequence of later uplift versus later downwelling. Moving forward in time, we get to the Permian Triassic era. And this I think is really the template phase of what we see in Antarctica today. Like most of the topography and the basins, you know, hark back to this era. And we have fundamentally the subduction zone heading out here in what most of us would call the east, but I'm going to call the west because it's this side of West Antarctica. And we've got the departure here of the Cimmerian terrains over this side. And this generates a very interesting system. We have ongoing rifting in here. We're in the prior basin, but we have this series of smaller basins forming throughout East Antarctica, and they seem to form in two structural sets. We have those that are essentially parallel to the, parallel, these are the green ones, that are parallel to the orientation of the Tethyan margin, and we've got the ones that are perpendicular to the orientation of the Tethyan margin. And these have connections, for example, the Perth Basin, probably connecting down into the Aurora Basin and also the Knox Basin, Mahanandi and Godavari connecting into Lambert and so on.
Great, Alan.
Yeah.
Need to wrap up.
Wrap up. Oh, I've spoken too much again. All right, very quickly. Gondwana phase, much better understood. So we have this series of departure events around the margin with basins forming on the sort of adjacent parts of East Antarctica. And then you can read that slide yourself.
Thanks, Alan. Sorry to hurry you along there. 10
No,
minutes.
that's okay. I should have learned to not talk so much.
Never enough, is it? We'll move straight along because we're going to have our Q&A session at the end. So thanks, Alan. And the next talk is actually by Alessandro Maritati, but I'm giving it on his behalf. So let me just open up my, can someone just let me know that that's coming through okay?
Yeah, that's all good, Jackie. Perfect.
Thank you. Okay, great. Okay, so as I said, I'm presenting this work on behalf of Alessandro Maritati, who was formerly with UTAS. And I'm going to show you some evidence for two basins, so it follows on well from Alan's talk, in the Knox Rift area that formed during supercontinent transitions, the first during Rodinia to Gondwana, and the second during the rifting of Pangaea. No, I can't progress. Here we go. So we know that subglacial basins exist across Antarctica, and there's this beautiful map that Alan has shown, which was just out last week by Lee and colleagues. And they're really key archives, both of the tectonic evolution, but also the ice sheet and the climate history. But although they host those valuable records, they're largely inaccessible to sampling, and so it is quite rare to be able to sample many of these basins. So in this talk, I'll show you some sedimentary material from the Knox Rift that's shown in that red box there, and the clues that these rocks might hold for basin evolution in the region. So the Knox Rift area, where is it? Well, it hosts the modern Scott glaciers and Denman glaciers that are in these deep troughs here. So this is topography shown here. And geophysical data, such as this ice cap gravity data here, suggests that there are thick accumulations of sediments in this area, up to 8 kilometres in the deepest part. But the only rock exposures that we know of are the Mount Sando and Mount Amundsen, which crop out in this basement highland here inland. And they comprise, those mountains comprise low-grade metasedimentary rocks that were deposited during the Neoproterozoic. And they've been related by Mikulski and colleagues to inliers along the Western Australian margin, along the Darling Fault. But we know from thermo-chronology that the main cooling event in the region that's summarised here occurred between about 300 and 200 million years ago. So it suggests that the rift itself is a Paleozoic to Mesozoic feature. So are there two basins here? Well, we suggest that the rift actually preserves the remnant Neoproterozoic basin inliers, as well as a thick Phanerozoic basin, and both of those are sampled by the modern glaciers. So we sampled in situ sedimentary rocks from near the top of Mount Sando, here's a photo here, as well as about 40 glacially transported samples. The Mount Sando sample that we looked at in detail is a greywacke. It's from the upper part of the stratigraphy, and these rocks have been described by Russian geologists in quite some detail. They're constrained to be younger than 1 billion years and overprinted at about 600 to 500 million years ago. The glacially transported rocks that we analysed come from a quaternary moraine adjacent to the Bunga Hills here. There's a photo. So we sampled this moraine here, but also some erratics from Cape Jones to the west, which is adjacent to the Denman Glacier. And these glacially transported samples, they don't resemble any lithologies that we can see along the coastline. And the present day ice flow suggests that they come down the glaciers from the Knox Rift area, ultimately. So we define two broad groups of the glacially transported rocks based on analysis of 7 samples. So we have group A here shown on the left. They're well sorted quartz arenites shown in red, with a craton interior provenance. And then we have group B on the right here. They're less mature, moderately well sorted, with a sublithoarenite composition and a recycled orogenic provenance. And they're more rich in garnet and titanite compared to the first group. So we looked at detrital zircon from across these samples, as well as the Mount Sando sample, which is shown in the top here. So Mount Sando has concordant data that has a main peak about 1.1 billion years and some older peaks as well. And that's quite similar to what's been published from Mount Sando before, and shown here in grey is the data from Mikulski and others from 2020. The quartz arenite samples, so the transported samples are shown at the bottom here, and they have a spectrum that resembles the Mount Sando rocks, with the main 1.1 to 1.3 billion year population or populations, and also a prominent 1.4 to 1.5 GA populations in at least 2 of those samples. So we can infer a maximum deposition age of about 1 billion, which is similar to Sandow for these glacially transported rocks. Group B rocks, on the other hand, they include zircons as young as 600 million years, and so that's a maximum deposition age for this group. But like the first group, they have a main population between about 1.1 and 1.3. But there are differences. We have some sort of 700 to 800, 900 million year grains and older than 2.5 billion, which is a key difference with Group A. So we looked at hafnium isotope data to try and discriminate the provenance between these 2 groups further. So we can see here's Group A, the main 1.1 to 1.3 population shown here. Have epsilon hafnium initial ratios that or values that go from about -5 to +8. And we have this clustered radiogenic population up here at 1.4 to 1.5 as well. And the coloured polygons in the back there, the blues, the purples, correlate with the polygons on the left and the map. And so as this representation highlights, the relatively radiogenic signatures of these detrital zircons overlap the Nuena Benzari and the Wilkes provinces from what we know from published work that's been published in the past from outcrop. And so we suggest that the Neoproterozoic Mount Sando group, that basin cycle represents detritus sourced from the east to the west, and that both the Denman and the Scott glaciers are actively eroding that material today. And these samples have very similar detrital zircon uranium lead hafnium signatures to sandstones that have been brought down the Vanderford Glacier to the east and shown, these erratics are shown where the green stars are there near the Windmill Islands, and some photos here. And overlain, you can see on the hafnium plot here, they're very, very similar in their character. So we suggest that that these rocks are all related, and the ones at Windmill Islands have been interpreted to be part of this a major inland basin that formed in the Neoproterozoic, which is partly shown here, and that's thought to correlate with the Officer Basin in Australia. And Group B is quite different. The hafnium data shows that the zircons are mainly negative. This main population has values down to about -13, and the young zircon have a spread, but are mainly between -10 and -20. So together they have a stronger affinity with the Bunga Hills block. You can see in the darker purple, which is exposed over here, which has a more evolved signature. There's no known outcrop of 600 million year old rocks in the Bunga Hills, but the Cambrian Ediacaran to Cambrian Kunga orogeny did overprint this area quite significantly. So we suggest that there may well be rocks of that age in the region. So we suggest this Knox cycle includes detritus sourced from the western rift shoulder. And based on the thermo-chronology, this occurred between 300 and 200 million years ago. So to summarize, I've presented evidence for 2 distinct episodes of basin formation here in the Knox Rift. Cycle 1 formed on the Western Australia-Antarctic margin during the transition from Rodinia to Gondwana, as shown in the top panel there. And then cycle 2 corresponds to the formation of the Knox Rift itself and the accumulation of Permian to Triassic sediments during what we think is during the rifting of Pangaea. The formation of the Knox Rift and the associated uplift at that time likely disrupted the Neoproterozoic Sandow sequences. So we see them today preserved as inliers in some key regions. And an analogue may be, if you're thinking of Australia, the Central Australian Phanerozoic basin, such as the Canning Basin, where there's Neoproterozoic sequences of the older Officer Basin that are exposed as inliers in that within those younger basins. So that's something we're looking to as an analogue. And that's my presentation. Thanks. I'll stop sharing. Okay. So our next speaker is Luca Magri. Luca's from the University of Tasmania and he's traveling at the moment. So we're going to have a recording of his talk. So IT, could you play that please? Have we got you there, IT? Yes, please.
Please. While they're getting that started, I haven't found one of the speakers, Sabal Gupta, in the list of participants. So if they are there with a different name under their Zoom, could they just let us know?
Everyone, the title of this presentation is Reefing the Australian Antarctic Margin, the Williams Ridge Broken Ridge sector. I'm going to present those study areas to you, showing you multi-channel seismic reflection data collected on different voyages in the past. Williams Ridge and Broken Ridge are two submarine ridges which are part of the same large igneous province. Large igneous provinces are massive emplacement of intrusive and extrusive rocks, which are predominantly mafic, and emplaced in relatively short period of time. In the image on the left in black, you can see the Kerguelen large igneous province in its evolution. It is almost 25 million km³ of material, and its development goes along with the interaction between the movement of plate tectonics and the impingement of the Kerguelen mantle plume. In the image on the right, you can see the Kerguelen Plateau Broken Ridge segment at present day, and in the red boxes, the two study areas of this study, which are Williams Ridge on the Antarctic plate and Broken Ridge on the Australian plate. The method we use for this investigation is the multi-channel seismic reflection. We have a seismic vessel with a source, which is the air gun, and a receiver, which is the streamer cable with hydrophones. What we do is sending acoustic waves, seismic waves within the water column, and record how long they take to go to a surface, to be reflected back and received by the receiver. The acoustic waves are reflected when there is a contrast of acoustic impedance. The acoustic impedance is typical of each type of rock or sediment package, and it's represented by the density of the rock multiplied by the seismic wave velocity. What is important is the reflection coefficient, because looking at the quantity of reflected energy, we can understand the difference between relative sedimentary packages of rocks. This study has begun with a literature review of the multi-channel seismic reflection profiles collected in Kerguelen Plateau and Broken Ridge. In the image A, you can see Kerguelen Plateau, and in the image B, Broken Ridge. And in both of them, the yellow and the red lines are the newly acquired seismic reflection profiles. The red one are the one collected by the RV investigator, and the yellow one are collected by RV only. The literature review enabled me to create a stratigraphic framework which represents all the horizons and sedimentary packages and rocks found in all the seismic profiles analyzed. In this study, I consider the time frame which goes from 100 to 35 million years, which are the pre-rift and sin-rift stage of the rift system. Within this time period, I find several horizons, which are the base of Cenomanian and Turonian, whether in Williams Ridge or Broken Ridge, the base of Campanian, the base of Maastrichtian, mid-Eocene, and the base of the Oligocene. The oldest unconformity we can find in seismic profiles in Williams Ridge and Broken Ridge is the one dividing crystalline basement and carbonate rocks, which is the Cenob, which is the base of the Cenomanian in Williams Ridge, and the Turb, which is the base of the Turonian in Broken Ridge. These seismic profiles collected in Labuan Basin, so we consider here the green reflector to be Cenob, which is more or less 100 million years. So the events that led to the creation of these unconformities are the combination of two. So the first is the global scale, the global plate tectonic reorganization, which led to the purely strike-slip movement of the Australian and Antarctic plate in this sector, and the movement of the Kerguelen mantle plume, which led to an increase of density and a collapse of the structure. So the combination of almost purely strike-slip movement and sinking of the crust led to the opening and progressive formation of the Labuan Basin. Another seismic profile collected in Kerguelen Plateau area is the legacy one collected in Williams Ridge by Geoscience Australia in 1997. Here again we consider the green line, the green horizon, to be the base of the Cenomanian, roughly 100 million years old. And there are two important things here to underline. The first one is the presence of flower structures within the basement, which is a sort of a proof of potential almost purely strike-slip movement between the Australian and the Antarctic plate at this stage. And the other important thing we can see here is in the green dashed line, dipping reflectors within the basement, which are thought to be either layering in continental crust or lava flows placed in the early stages of the emplacement of the large igneous province. If we consider a broken ridge seismic profiles collected by RV investigator, with the green horizon here we refer to the base of the Turonian, which is 95 million years, and again we can see flower structures within the basement, which is sort of again a proof of a basement of broken ridge already in place during this stage of deformation. And very important, for the first time we see also on the other end member, which is broken ridge, dipping reflectors within the basement. The unconformities from 83 million years to 34 million years are the same in Williams Ridge and Broken Ridge because the end members are thought to be contiguous at the time, so sharing the same story. At 83 million years, we have the base of the Campanian as unconformity, which represents the interruption of the Labuan Basin opening due to seafloor spreading onset in the Great Australian Bight. This unconformity is an horizon within carbonate rocks. At 70 million years, there is the base of the Maastrichtian unconformity, and this horizon is derived by the rift onset of Williams Ridge and Broken Ridge system, which is reflected by the uplift of the entire region. So this unconformity is an horizon dividing carbonate rocks from sediment. At 43 million years, the mid-Eocene unconformity is representing the breakup between Williams Ridge and Broken Ridge, which is a really, really strong reflection. And this horizon is within sediment. And then at 34 million years, there is the base of the Oligocene, which is the unconformity representing the end of a stabilization phase started from the breakup of Williams Ridge and Broken Ridge and lasting until the pure subsidence stage. This unconformity is an horizon within sediment. At this stage, I would like to show you 8 seismic reflection profiles, 4 collected in Williams Ridge and 4 collected in Broken Ridge, reconstructed at more or less 43 million years, using the pole of rotation of Whittaker et al. 2013. Reconstructing these seismic profiles, we can see they are kind of matching each other, so it is easier to see similarities and differences between those. The first example that I want to show you is Williams Ridge profile number 3 and Broken Ridge profile number 6. As you can see, they show similar characteristics with the main rift shoulder and another rotated block oceanwards. Going towards southeast, we have Williams Ridge profile number 4 and Broken Ridge profile number 7. These seismic profiles shows asymmetry. Although we have a prominent rift shoulder in both of those, in Williams Ridge we have a rotated block present oceanwards, which is not present in Broken Ridge. Further southeast, analyzing Williams Ridge profile number 1 and Broken Ridge profile number 8, we can notice that the symmetry is back with the prominent rift shoulder on both end members and also with the presence of the rifted rotated block. In the southeasternmost part of the system, Williams Ridge profile number 2 and Broken Ridge profile number 9 show a significant difference from what we saw in the past. In this case, we have the lack of predominant rift shoulder and rotated blocks, and the seismic profiles are characterized by horst and graben mainly. In summary, what we have been finding so far is a division we can see in the seismic profiles between a pre-rift foundation, an older part which is characterized by a crystalline basement deposited until 195 million years, and carbonate rocks deposited between 170 million years. And then a second part, a younger part, which is a syn rift in fill, which is characterized by sedimentary unit deposited between 70 and 34 million years. I just want to put here some references of the things I've been talking about, and thank you all for listening.
Thanks, Luca. So now we'll move to our final speaker in this short block, Jeremy Azelmas, who's joining us from the University of Tasmania. Jeremy, you're able to share your screen?
Yeah. Can you see it and hear me okay?
Almost. Yeah, do you want to just put it in presentation mode?
Yep. Is it in presentation mode now?
No, there might
No?
be a delay. Now I've got it. Yep, I've
No,
got
okay.
it.
Yeah, that's a bit of delay.
Thank you, Jeremy.
All right. Hello, everyone. Today I'll be presenting some zircon and apatite work we've done from some dredged continental rocks at Williams Ridge in the Kerguelen Plateau. So the Kerguelen Plateau is a thick, large igneous province in the Indian Ocean. It's dominantly comprised of these plume-derived basalts formed from the Kerguelen plume, which is this dotted area here. The Kerguelen Plateau started forming around 120 million years ago when the plume impinged on the newly forming Indian Ocean. This coincides with the breakup of East Gondwana, and it's kind of a chicken or an egg situation if the plume caused the breakup of East Gondwana or if it was an artifact of the breakup. The jury's still out on that one, I think. So the Kerguelen plume has continued to put out volcanism since 120 million years ago to the modern day, but the bulk of the Kerguelen Plateau formed during the Cretaceous. So the southern section of the Kerguelen Plateau formed around 120 million years ago. The central section and the Eland Bank section of the Kerguelen Plateau formed around 100 million years ago. And recently, the northern section of the Kerguelen Plateau formed around 30 million years ago. So here are those divisions on a modern map of the Kerguelen Plateau with the north, central, and southern sections. Despite its location within an ocean basin, there's actually a lot of evidence to indicate that there's continental crust somewhere in the Kerguelen Plateau. There's been a few seismic studies that indicate that there's stretched continental crust at depth beneath the plume-derived basalts in the southern section of the Kerguelen Plateau. There's also been several geochemical studies on the basalts that show the geochemistry and the isotope geochemistry of the basalts are quite distinct from mid-ocean ridge basalts. For example, they're depleted in niobium and they have strange lead isotope ratios, which are indicative of continental crust assimilation in their source for the magmas. However, the only real tangible evidence for continental crust in the Kerguelen Plateau comes from this area here, which is Eland Bank. Here they cored Eland Bank and they retrieved a fluvial sandstone that contained clasts of continental materials such as granite and gneiss, which they interpreted as proximal to the source. So in 2020, the RV investigator journeyed to the Kerguelen Plateau, and for the first time, they sampled Williams Ridge, which is highlighted by this red polygon in the eastern Kerguelen Plateau. And they sampled the bedrock there for the first time. They dredged up a high amount of continental crustal rocks, So in this talk, I'll describe the dredged material at Williams Ridge, and I'll also assert that Williams Ridge is underlain by continental material, similar to Eland Bank. So there were 13 dredge locations at Williams Ridge and the neighbouring rig seismic seamount. Pretty much all of them retrieved both continental crustal rocks and also these plume-derived basalts. Dredge 12 and Dredge 13, they exclusively retrieved these plume-derived basalts, though. As you can see, the dredged material is actually quite large. Here's some continental rocks, and there's some oceanic plume-derived basalts there. So the retrieved dredged continental rocks, their rock types are actually quite diverse. We have some sedimentary rocks like metasandstones. There's a range of plutonic rocks, ranging from diorites to granitoid in composition. And there was also several metamorphic rocks drenched. There were plenty of orthogneisses, and there was also some metapelates. So we chose 14 of these rock types to do some zircon and apatite work on. And I'll go through this, the geochronology of this K-Feldspar by gneiss now, because it's quite typical of the Williams Ridge rocks. So the zircons retrieved from this K-Feldspar by gneiss, they were quite complex in their texture. They had blurry to convoluted zoning in their cores, and they also had these bright, thin CL rims that were too small to get a laser spot on. When you date these zircons, most of them are quite concordant, but a few of them are somewhat discordant and they form a weak lead loss trend. So that means we've got a very nice upper intercept age, which we interpret as a emplacement or crystallization age for the protolith to this gneiss. But it means we've got a metamorphic age, which is the lower intercept of this Discordia has very high error. So for example, this metamorphic age is plus or minus 100 million years. To kind of better constrain the metamorphic age, we did some apatite dating. This is quite typical of all the apatite dating we've done. The apatites are quite texturally homogeneous, and they have medium to high common lead, but they do form a nice lead loss Discordia, which indicates the metamorphic age at the lower intercept. So summarizing all the geochronological information that we retrieved, it's summarized in this figure here. These red diamonds, they indicate either the crystallization age of igneous rocks or the crystallization age of protolith material to metamorphic rocks. They're quite variable in the ages that they retrieved. However, what's less variable is the metamorphic zircon ages, which are these purple diamonds, and also these blue circles, which are the apatite metamorphic ages. So putting this all together, we can kind of classify the rocks into three groups. We have these quite young diorites down here, which we don't think are actually continental material. We interpret these as plume-derived diorites, probably, since they're so young. And then we also have two suites of continental rocks. The first being rocks that have a metamorphic age around 500 million years old, and rocks that have a metamorphic age around 1150 million years old. So these age ranges, they match the 500 million year old age range matches the ages for the Kungur orogeny, and the 1150 million year old ages match the zircon ages for the Australo-Antarctic basement. So if we were to consider Williams Ridge as a microcontinent and reconstruct it to see where it came from, we might reconstruct it somewhere around here. So this figure depicts a tectonic plate reconstruction to the late Jurassic, where the Kerguelen Plateau was starting to form, and also the breakup of East Gondwana was occurring. The red area indicates Australian and Australo-Antarctic basement areas, and the green areas indicate Indo-Antarctic basement areas. So from our age ranges of 1150 and around 500 million years old, would have to have our microcontinent kind of somewhere in here, so it gets that Kungur orogeny overprint, as well as the Australo-Antarctic basement ages. This varies a little bit to the Eland Bank microcontinent, which has age affinity more like more like Indo-Antarctic basement. It does have this Kungur orogeny overprint at 550 million years, but also some of the zircons at Eland Bank date to around 900 million years old. Okay, so you're probably wondering how you would form this microcontinent. You need a series of ridge jumps, and the ridge jumps would have to jump into a continental interior and rip off a part of the continent and isolate it in oceanic crust. The processes that you can achieve these ridge jumps, they have been interpreted by a few different processes. The first process kind of focuses more on plume ridge processes, and this has been used to describe the formation of the Eland Bank microcontinent. Here, a plume next to an existing mid-ocean ridge the mid-ocean ridge becomes extinct because of the heat and enhanced upwelling from the plume, and this causes the mid-ocean ridge to jump landward, and this could jump to within a continental interior, and as it's rifting, rift off a piece of that continent. However, there is another hypothesis which is thought to form the Golden Drac and Batavian Knoll microcontinents. These are also formed during the breakup of East Gondwana, and that's tectonic reconfiguration and reshuffling. The stresses on that caused some of the continental exterior to be carved out during the breakup. So this is where my research is kind of heading, is to assess these two processes in the formation of the Williams Ridge microcontinent. Okay, that will be all. Thank you.
Jeremy? Nathan, did you want to host the...
Happy to, Jackie, thank you. You muted yourself halfway through the sentence.
Sorry.
So passing over to me.
Get the gist.
Yeah, but thank you for the 4 speakers. So we've had 2 great talks on sedimentary basins and 2 great talks related to the Kerguelen Plateau. There's a question for Jackie in the Q&A that hasn't been answered yet. I'll start with that one while people can type in questions into the Q&A, or they can raise their hand and we can allow you to speak if you want to ask your question in person. So starting with Jackie there, thanks for a very interesting talk. Any thoughts on the reason for the shift in provenance in the 2 lithic arenites?
Yeah, so we had the 2 groups of transported samples. One of them was the quartz arenites and one of them were the sublithic arenites. And so within the sublithic arenites themselves, I think there was 4 samples in that group. The provenance was actually quite similar between the samples. So they had that young 600 million year old group of zircon. And with the hafnium, that allowed us to fingerprint the proximal Bunga Hills type crust for those young zircon. And then they had the 1.1 to 1.3 billion year old peaks as well, which was the main component of the zircon record. So I would say within that sublithic arenite group, the provenance was very similar. Definitely between the sublithic arenites and the quartz arenites, we have the big difference in provenance, and we relate that to 2 different basin cycles. So the quartz arenites being part of the Sandow group cycle, deposited in the Neoproterozoic, and then the sublithic arenites being part of that Phanerozoic basin, the Knox cycle. So we have the shift there between the 2 groups, but within the groups, they're quite similar.
So Jackie, I had a related question to that, and it was about the sort of westward movement of the sediment for the Sandow group, and then the eastward movement of the sediment at a more local source for the second lot of rocks. Is there anything that you've interpreted in terms of the tectonic scenarios at the time that made anything of that change in direction of sediment source?
Yeah, so I believe it's the other way around. So the older sediments we think are derived from the east, so the sediments moving west. And so at the time that in the Neoproterozoic, this basin, the Sandow group, was forming on the edge of the Australo-Antarctic craton. Alessandro has a hypothesis that the Sandow group itself actually records passive margin to an active margin as you go up stratigraphy. So that's an interesting idea. I'm not sure if we have enough samples to make that convincing at the moment. but we have that basin forming on the Western Australo-Antarctic margin. And then for the Permo-Triassic phase, the Knox Basin phase, we think that there's evidence in the thermo-chronology for this exhumation of the western shoulder of the rift, and so it would then make sense that that becomes a basement source for the basin infill.
Thanks, Jackie. Alan's raised his hand and now unmuted. So Alan, do you want to contribute? Hello, Alan, you're unmuted, but we can't hear you. All right, maybe we'll move on to Nikita, please, if you've got a comment.
So I have a comment or rather question for Jacqueline. So we still not published our results for Western Denman Glacier outcrops. There we get 500 million years plutonic rocks, which are sienites or kind of this, which marks the rifting process. Very huge. It takes the area from the west, from Baldwin rocks on the West Denman Glacier until the Hippo Island. This is huge plutonic.
Nikita, sorry to interrupt, but your audio has dropped very quiet. Can you just repeat the question?
Yes, so sorry for that. So I have a small comment, not a question. So we still not published yet our new geochronological results on Western Denman outcrop. But I should inform you that there is a huge plutonic intrusion made up of sienites or high potassium magmatic rocks, which indicate the rifting process at 500 million years ago. And so it's very interesting because it can be related to the change of sedimentary rotolites, which you talked about. And Jeremy, so I want to ask something, Jeremy.
Go ahead.
If he is. Jeremy, so I've just noticed that you studied geochronology of Kerguelen Plateau, and so I just want to say that it's related. So your results are related to Mirny Station, which I'm going to report next time. So, and more interesting for us is there is basic intrusions there, huge provinces in Kerguelen Plateau, and there is some traces of that in Mirny Station area, because we have new geochronology, and it's around 800 millions for basic rocks. So you can find that in Michalski publications before it came earlier. So and this geological history. So you collected several zircon samples and get geochronological results. They are correlated to Mirny Station area, but Mirny Station area is more related to Rainier provinces, and you made a map where the Kerguelen and Mirny Station are together with Albany, Fraser, and Wilkes. So perhaps,
do you want me to share the map?
Sure.
Yeah.
So perhaps it can be this.
So this one.
somewhat, yes, but the map is very nice. Whether it's published somewhere or not, do you know?
Yeah,
S-
yeah. This one was published by Alessandro Marititi, who, Jackie, was that who you were presenting for?
Yeah, that's right. Yeah.
So, but so so you have NPJD.
Your audio has gone quiet again.
Sorry. So I'm something hello. Okay, I'm here. So sorry.
Oh,
So
there we go.
my
Yep.
is that so you painted as red the area of NP, JP, and Mirny station. So you see this Mirny fault. It's always a problem where it comes from. So because it's Mirny geology is related to perhaps they are related. Kerguelen plateau is related to NP. This Shillong plateau. Where is Kerguelen? Sorry, I
So
didn't.
this is the northern section of the Kerguelen plateau. It's still pretty tiny at whenever this was reconstructed too. So
Yes.
in here in the ocean, the NP.
So perhaps the Mirny fault can be continued onto the north and to the Shillong plateau somewhere here, because this Mirny has a little bit different geology. It's like green most of all. So,
Yeah.
But this is
so
inferred from
I believe.
Jackie?
Then.
Yeah.
I think we'll have to move on, but yeah, thanks for that. And let's chat about that in some more detail. It's really relevant,
Yes.
Nikita. Thanks.
Yeah.
Thanks very much for the questions. So we're now moving on to the second part of this first session. So we've got 4 more talks. The first talk is from Alexander or Sasha, and I believe that we're having a recording. So IT, could you play that for us, please?
Sorry.
Hello, Sasha. Would you like to give the talk live, or you wanted to play the recording?
Please, I prefer to have a recording.
Okay. IT, can you please do that? Thank you.
I would like to inform you about posted map. Dear colleagues, today I would like to inform you about posted map 2 our magnetic service, which allow to reduce coverage gaps in East Antarctic. This slide shows the results of ADMAP 2 compilation. To the left we can see the coverage map. Blue lines belong to ADMAP 1 and red lines were added by the second edition of the map. The ADMAP 2 compilation matched the near-surface magnetic survey data collected mainly between the IGY 1957 and 2013. The map reveals a wide variation of magnetic anomalies reflecting crustal terrains of different lithologies and rock magnetic properties, ages, geothermal attributes, and degrees of tectonic reworking. This image shows post-ADMAP 2 service. Since the release of ADMAP 2 in 2017, the international Antarctic geomagnetic community remains very active in crustal magnetic anomaly mapping. Almost 700,000 line kilometers of new air and shipborne data have been added to 3.5 million line kilometers of the previous database. Many of these new surveys were completed by major international programs and multidisciplinary projects. The neuromagnetic data provide key coverage of the recovery basin and the South Pole region, southern Prince Elizabeth Land, and the Ross Ice Shelf, and other poorly investigated Antarctic regions. Some surveys are currently proprietary and hence cannot yet be combined with existing publicly available datasets. This slide shows results of the ice graph survey that is superimposed with the ADMAP2 compilation. The coastland crust includes key pissing points for reconstructing linkages between East Antarctica and the Laurentian mid-continent rift system within Rodinia. It also hosts the inferred remnants of the major suture zone active during Gondwana's amalgamation in Pan-African times. The recovery ice grave survey of the major ice streams was flown in a Danish, Norwegian, UK, Argentine collaboration that collected some 24,000 line kilometers of laser altimetry, ice probing radar, gravity, and magnetic data. The new data of the largely ice-covered recovery and glacier catchments helped to map the extent of major subglacial faults and thereby delineate the tectonic boundaries of the coastland, Shackleton Range, and Ronin Maudland crustal provinces. The Polar Gap Airborne Survey covered the so-called Pole of Ignorance with the reconnaissance airborne geophysical data. The primary focus of the European Space Agency's Antarctic Airborne Polar Gap Survey was to obtain high-quality airborne gravity data for the polar cap south of 83.5 south to help augment the lack of satellite gravity coverage by ESA's Near-Polar Orbiting Gauche mission. Some 35,000 line kilometers of aeromagnetic and ice-penetrating radar data were also collected. One of the largest datasets was collected by the Alfred Wegener Institute in collaboration with BGR. In total, they gathered about 125,000 line kilometers of aeromagnetic data in and around Ronin Maudland and other regions. For example, they completed two surveys of the Foster magnetic anomaly. The survey data were combined with previously survey profiles to reduce the effective line spacing of the profile coverage from 10 to 5 kilometers. Interpretation of this data will offer new insights on the amalgamation of Gondwana. In the eastern part of Ronin Maudland, a large campaign of nearly 30 survey flights was carried out over the Sorondana Mountains and neighboring regions. Aeromagnetic data offer further insights on the southern and eastern extents of the Tonian Ocean arc superterrain. These surveys results helped to constrain the amalgamation of Gondwana from multiple volcanic island arc collisions between the ancient continental cores. The Ross Ice Shelf is one of the largest regions of ignorance because very little aeromagnetic surveying has been acquired here since the pioneering aerogeophysical survey of the 1960s and 70s. These early surveys were mainly flown as transit to, from, and between the main survey areas. But the situation changed dramatically in 2013 when the Rosetta project conducted free surveys. Magnetic anomalies from the Rosetta highlight a major crustal boundary between the rifted edge of East Antarctica, which may extend significantly further west than generally assumed. This slide shows the result of the two aeromagnetic surveys of the Bailey and Recovery glaciers in the coastland area. In general, 5 airborne radar and magnetic surveys were carried out within Filchner Ice Shelf System project. The major goal of this project was to investigate how the Filchner ice shelf might respond to a warmer world, and what the impact of sea level rise could be by the middle of this century. Over the 5 seasons, Chinese scientists surveyed one of the largest gaps in data coverage located in southern Prince Elizabeth Land. They collected more than 120,000 line kilometers of aeromagnetic data. It should be noted that both the IceCap Eagle and IceCap Pale projects maintain active in East Antarctic regions through international collaborations of scientists from Australia, China, France, Italy, South Korea, UK, and USA. Comprehensive aerogeophysical mapping of southern Prince Elizabeth Land provides the first look at the gross lithology and large-scale structural geology of the Central Antarctic Plate, which is the keystone for tectonic reconstructions. It clearly can be seen on the right image that the obtained data contain distinctive noise or corrugations that must be excluded by additional processing efforts. The RAE 1667 airborne service for the Eastern Prince Elizabeth Land and Queen Mary Land in 2013-2022 collected more than 40,000 line kilometers of magnetic and ice probing radar data. From our point of view, this service provided new constraints on the future between Indo-Antarctica and Austral-Antarctica that ran south-southeast from the Scott Glacier inland in accordance with Aitken et al. 2014 interpretation. It's been argued that the India-Australia paleoplate boundary may pass through Antarctica close to the Milne Station, because it appears to correspond to an unnamed subglacial fault identified by Aitken, which intersects the coast near 94 Great East. However, new detailed Russian bedrock topography and magnetic anomaly data mapped to the Milne Station's east clearly fail to observe Daczko et al. 2018 dubbed Mirny fault, so that the location of Kunga's future remains enigmatic. And last image demonstrates air and shipborne magnetic coverage that we have at present in Antarctica. Red lines were collected in recent years. We can see that major gaps in East Antarctica are more or less covered by recent surveys. However, we still have a little amount of data in many regions, including southern Enderby Land, in areas around the Gamutzev Mountains and the Lake Vostok, as well as over Adelaide Land, which is of crucial importance for tectonic reconstructions. This is all. Thank you.
Thanks, Sasha, for that presentation. So we'll hold questions to the end of this block, and hopefully you can join us in the Q&A. Is that okay?
Okay.
Okay, thanks. Our next speaker is Nikita Borokov. Nikita, could you share your screen and go ahead, please?
So I did. Hello, everyone. I'm really delighted to be presented here in our session. So, and I'm sharing our preliminary results on geological evolution of Mirny Station area. So, and
We
this
just
is
can't see your screen yet. Sorry, Nikita, we can't see your screen.
you
Can you try sharing your screen again?
yes.
Remember
Sure.
how we practiced before?
Sure.
Yeah, with the,
So sorry for that. So I
okay.
try to share. Yes, I
Yeah.
should do this presentation. So sorry for that.
That's good. And then if you put it in the full screen, that's perfect. Thank you.
So sorry for that. So geological evolution of Mirny Station area, our preliminary results, and this is how it looks like. Some outcrops, some stones and islands. So you can see. This is to illustrate briefly the geology of East Antarctic, which is made up of Archean and Paleoproterozoic nucleus divided by Mesoneoproterozoic orogenic belts, and position of Mirny area on Pravda coast is here, and it is very crucial here because we have to know the geology of Mirny Station to understand where this division and fault can be traced between the Wilkes province and Rainer province. So, and here I just collected results from new tectonic and geological data, and to represent the position of Mirny Station area. So, and as we already know, it can be related to Great Indian orogeny and Rainier complex. So, and that is why we decided to collect samples there and perform new geochronological measurements. So this is geological scheme of Mirny Station area. To illustrate it, here it's made up of a metamorphic complex, which is Rainier complex, and a new 500 million years intrusives, which is made of charnokites and diorites. So, and some mafic intrusion. So this is main position. So if we back here, so this is main outcrop, which is available to collect samples. So here we have a metamorphic complex, which is made up of different migmatites, which embedded granulites and mafic granulites there, and some charnokites intrusions. So, and we collected samples from each complex and made geochronology. So it's how outcrops looks like. So this is outcrops corresponding to related to charnokites here and here. So it's very difficult to collect. But anyway, metamorphic complexes is seen and are available to study. So let's start from magmatic complex and charnokites. These charnokites are, they have a composition of orthoperoxene bearing monzodiorites and monzonites here. And here we can see the contact between a metamorphic complex of Mirny Station area. This is granite, feldspar gneisses, migmatitic and mafic diorites intrusions. And here we can see some charnokites and which are intruded to the metamorphic complex. So here we can see how metamorphic complex looks like here in Mirny Station, and we can observe the main metamorphic body made up of garnet, feldspar, orthoperoxene bearing gneisses, and mafic granulites. So this is these are mafic granulites, which are also they represent budines, and they are also migmatized there. So in just the view of migmatization there of so we can see the different types of migmatites and neosomic granites. So we dated this part and this part. On this picture, we just I show you where we collect samples. So, and we obtained geochronological results from two different mafic granulites, and of course from the bedrock from budines and from the gneisses and plagiogneisses, and from the neosome and mesosome, and from dikes. So our preliminary results, just to illustrate a thermodynamic modeling for our samples. And we use the TERIAC domino program to get the results. So, and as you can see, we used the modeling and some different orthoperoxene and garnet orthoperoxene, different thermal barometers and geothermal parameters, and so we can see that the peak metamorphic event is happened at 700, between 700 and 800 degrees under the granulate conditions. And we also can trace different phylogenetic associations. One is relic and one is new. The relic is related to 800, 900 million years, and the new one is just traces of Pan-African orogeny. These are results. So we made a geochemistry of zircons and their morphological parts, and we just get some results on gneisses and plagiogneisses. They are not so they're very difficult. So we can see here that the protolite age, and protolite according to zircon geochemistry is mafic or middle magmatic rocks. This event around 1,800 and 900 years, the first event, and these reams and different metamorphic reams are corresponded to 500 years, as we can see here. So, and cores are represented by oscillatory zoned metamorphic zircon. So as you can see these results. So, and black rings, they are supposed to be metamorphic according to geochemistry. And here we have the results. So we get a metamorphic age of mafic granulites, which are from budins, and they are around 500 million years ago. And we also have for some samples, we can get a protolites, which are also mafic, and we can trace the beginning of crystallizations. And for some results for plagiognesis also indicates some granulitic like sector zoning zircons, which indicates the metamorphic event according to zircon geochemistry, of course, metamorphic event at 500 and protolite crystallization at 1,000 million years ago. And as we have huge data on geochemistry, we decided to use discriminant diagrams for mafic rocks and granulites, and we divided them into groups which are geochemistry related to different tectonic events. So, and as you can see, we plotted different magmatic rocks from Mirny Station with charnokites and mafic granulites here, and we divided them according to their geochemistry and tectonic position here. And for mafic rocks and mafic granulites, we, according to their geochemistry, they are like enriched morphs. So as a result, we are always creating such a correlation scheme with Mirny Station area here and Bangor Hills, which we discussed, and Rainer province. So, and it's always under construction because we're waiting new geochronological results here. So, and we can trace that this event happened with intrusions of charnokites and mafic intrusions also, and mafic intrusions here, but they are overcame metamorphic processes at 500 years. But anyway,
Nikita,
so my results, sorry.
um,
Nikita, we've lost your audio. We do have to wrap up now. Sorry, we've lost your audio again. Do you have a summary slide you want to finish on to just show us the last slide? Yeah, we've lost your audio again.
So, sorry.
Could you
Sorry.
flick? Yeah, that's better. But we have gone over
Sorry.
time now. Could you flick to your last slide, because we are going to
Sorry.
have to.
Okay, sorry. So I am finishing. This
Okay.
is neodymium and samarium is isotopic diagram for Mirny station. So and Albany Fraser. So they have the same history, and they doesn't have the same history according if we study the first the GM and the history of isotopic systems, so the Albany, Fraser, and Wilk, they have a little bit more different history, and this is DM ages, and Mirny station are more related to Rainer province. So and here, so as just demonstrates that at this point it's more related with granulitic metamorphism and migmatization and Chernokites to Rainer provinces. So and I'm delighted to present you more results, but the time, and thank you for your attention, and you are welcome to many questions, and it would be great pleasure to answer and discuss.
Thank you, Nikita. We'll hold questions to the Q&A part, but if you could just stop sharing your screen now, please. So our next speaker is Saval Gupta. Welcome, Saval.
Can you hear me?
Yeah, perfect. Could you share your screen?
Okay. Right.
Thank you.
All right. You see my screen now?
We can.
And the presentation?
Yep, that's perfect.
Right. Okay. So thanks for giving us this opportunity. So this is a new group in a sense that has started working on the Antarctic fairly recently, and for that I speak for myself. I'm the third in the sequence mentioned here. Chandra Chatterjee is the first author. He's doing his PhD on the area. We have two veterans on this. One is Professor Naresh Pant of Delhi University, who's been working on this on Antarctica for a very long time. And Dev Samriddhi Arora did a PhD fairly recently on this area. So she did the metamorphism and petrology. And what we have been doing is supplementing this with some additional information which we think would help us to resolve something that we see in one of the reconstructions of Antarctic in Precambrian supercontinents. Now, talking of supercontinents, we just move into the context of the three that matter here. One is Columbia, which is supposed to have been approximately 1.5. I mean, all these aids differ with different people's preferences. Rodinia, which is a little better accepted to be around 1 GA, and Gondwana, which is around about 0.5 GA. Now, in all of these reconstructions, you can see the eastern part of Antarctica, right, has been related to some part of this green stuff, which is India. And this stretches through from Columbia to some reconstructions of Columbia, almost uniformly in all reconstructions of Rodinia, and a few in the Antarctic. Now, the basis of these reconstructions is really linking the eastern coast, the present-day east coast of India. So this is the Bay of Bengal, this is the Arabian Sea, this is the Indian Peninsula, with the Enderby Land, predominantly part area of East Antarctica. So this is Princess Elizabeth Land, this is Enderby Land. And what people tend to have correlated would actually range mostly on the basis of a graben, which passes through the northern part of this EGMB, which is the Eastern Ghats Mobile Belt. It's a granulite province of Neoproterozoic age, and it's basically 1 GA, starts at 1 GA, and most of the events that are thermal events that are recorded here stretch up to the Pan-African. However, we have a rift in the northern part of the Eastern Ghats, and that rift is called the Mahanadi Rift, which hosts Gondwana age sediments. So you have sediments stretching from Permian right up to the Cretaceous hosted within this basin, which was probably why they are correlated with what Mawson reported from the Antarctic, Gondwana sediments here. And later on, later work has, through the 80s especially, actually demonstrated that there was a lot of similarity between what we see in the Eastern Ghats Mobile Belt, which is these granulites of some of them having very high temperature, imprints of very high temperature metamorphism around 1 GA, with what was seen in the Rainer complex of the Antarctic, right through into Prince Bay and some parts of Princess Elizabeth Land. Now, our contention has been to actually see whether this correlation really matters. Because although this correlation has been done primarily initially on the basis of the Gondwana sediments, but later on the basis of the metamorphism, which is much more widespread in the basement, the problem is that the link doesn't really end there. You see, the first thing is that how do we know that this is how India and Antarctica did actually fit together? Why is this postulated to be the fit? And the old reasons that were given was obviously the first one is the Gondwana sediments. The second ones are the granulites with an ultra-high temperature, some of which have ultra-high temperature imprint, which means that they experienced crustal temperatures in excess of 900 degrees centigrade. Subsequently, round about 650 to 450 or so, it's the broad span of what's defined as Pan-African. There has been reworking of the granulites at varying grades of metamorphisms. There are varying postulates. All of this granulite belt actually is fringed by cratons which are of Archean age. The problem is, even though these correlations stand, the problem is that if we think about this kind of basement actually extends into much of East Antarctica, in fact, some part into northeastern Antarctica, and a major part of this is Dronning Maudland, one of the second Indian stations that we have there. So the problem is, how do we know precisely which points actually fit? I mean, can it be done simply on the basis of metamorphism and geochronology? And I've always considered, and which is why I entered into the Antarctic problem. I have worked for over 30 years on the Eastern Ghats. So what I think is that this can't be done solely on the basis of the metamorphic and geochronological signature. It's not sufficient. So what we've tried to do is to use an additional geological signature, which is based on structural geology. We use the fabrics that are present, correlate that with the metamorphism and the geochronology, and see if we can fit that across the continents through all this area. Now, the key to this is really this fit that we see. And one of the things that was recently done by one of my PhD students in the Eastern Ghats belt was this entire granulite belt in the northern part. You actually have a wide extensional shear zone, which has reworked the granulites, which hasn't actually transformed most of the granulite assemblages, but what it has done is actually put in structural signatures, which actually swing all lineament trends, and you can only detect that structural signature through the deformation characteristics of the mineral fabrics that you can see, primarily quartz and feldspar. So if you actually reconstruct the metamorphic history within this red box, what we can actually see is that you have old deformation fabrics in which quartz and feldspar actually share grain boundary migration recrystallization structures. You have very high temperature assemblages, right? And these have been correlated with an early shortening deformation, which has resulted in crustal thickening, accompanied by granulite fascist metamorphism. We think that the peak conditions actually outlasted these shortening deformation, and these are estimated to be in excess of 900 degrees centigrade, right, at pressures which are, well, moderate to high. And this was around about 955 to 28 MA. Following this, there was a period during which you had some infiltration of hydrous fluids. Now, we just correlated it tentatively on the basis of monocyte chemical ages with this kind of age here, which some of which I think I saw in the previous speaker's talk. Following this, what is seen in the northern part of the Eastern Ghats belt is that all this swing in structural trends is because of a widespread extensional deformation, which was dominantly extensional with a component of sinistral shearing and plant view. So what that tells us is that the deformation microstructures tell us that the temperatures and even the reset exchange thermometers tell us that the temperatures were around about 550 to 600 degrees centigrade, mostly in the middle and fibulite fascies. Following this, again, you had an even lower temperature, even more localized, very sharp dextral strike slip fault, which operated under Greenwich fascies conditions, and this was again estimated to be around 515. So you have a complete sequence of events in which the structure and the metamorphism are together integrated into one consistent tectonic framework for the northern part of the Eastern Ghats. So if this actually matches what we see in the Antarctic, it should correlate with what we see in this area here, which is in East Antarctica, right, near to Pritz Bay. And the area that was predominantly worked on was the Larsen Hills area. And this was done by two of the co-authors in this study. One is Dev Samriddhi Arora, who did much of the petrology and metamorphic petrology in detail, and Chandra Chatterjee, who's just begun doing his structural work there. So we're still awaiting Chandra's samples, which haven't yet come back from South Africa. There's some problem because of the shipping routes being disturbed. Nevertheless, the structural data and the few samples that he managed to sort of smuggle through Indian customs tell us that we're dealing with a few areas that the structural data collected from the Larsen Hills area, including Batangan, from the Stones, the Grosvenor, Brathnefet, Stinier, and the Brockness area. And we have samples also from Easter Island and data also from Fisher Island, which is actually a major part of what we see here. Now, these are roughly what the outcrops look like. I haven't been to the Antarctic, so it was astonishing for me to see that there was such little ice there. So these areas seem to contrast very sharply with many of the other speakers, many of the other speakers were showing. But it's good in a sense, while it's bad for indications for global warming probably, but it's good for the geologists. You see a lot of rocks here. And during that, Chandra was doing fieldwork, collecting samples, mostly oriented samples from all of these areas, Brathnefet, Stinier, Rheinbold, Rottnest, and also Easter Island. So during these, then what he reconstructed was a structural fabric map from most of the Larsen Hills. And as you can see from the Batangan area, this is the penetrative fabric that actually dominates the rocks in the area. So this is a representative plot. So the data are far more than what he's actually represented here. So when you see all of this, you can see that there is a general swing in the structural strength. So you have south to southwesterly plunging foliations steeply here. You have very shallow dipping foliations in this part. You have foliations which are steep, but which are actually dipping the other way here. And here there is a clear sign of foliations dipping across each other and also showing a swing, which actually gives you a sort of trend in structural fabrics, which actually indicates a broad trend of change happening within the Larsen Hills itself. Now, if we look at the penetrative lineation, so these are arrowed now from the foliations that you can see that there are lineation patterns also differ very starkly. Now, most of the lineations that have been plotted here appear to be stretching lineations, so they would roughly correlate with the x direction of the strain ellipsoid, which in our senses what we are trying to do would be to correlate these with the transport direction that we can actually see from these rocks. And what are these rocks? So these are the things that we can actually see. So this is from North Grosvenor. So you can see a gneissic layering. It's very common in any people working in gneissic terrains like this. You have a gneissic layering, which is isoclinally folded. And as a result of these isoclinal folds, some of which you can actually see here, you have an S2 fabric, which is penetrative. So dominantly, S1 and S2 everywhere are parallel and practically indistinguishable. What you can see a lot of S2 planes on which you see this intersection lineation, which also corresponds to the—
Sorry, Cybal, can you wrap up? Can you wrap up too?
Okay, I'll just go quickly here. So
yep.
You can actually see, I'm sorry, I think I just overlooked this part. You have, you can see that these are parts where there is superposed deformation here, which tells you that after 2, you had 3 more deformation events, right? So following this area. So when you look at this, then you have a sense of a thrust, you have extension actually following it. So what we think is that the change in the structural trends is brought about by an extension, and these actually are represented in the field by these folds on the D2 foliation and these shears which act through these rocks. So we suspect a 4th one right at the south, which is a very localized shear zone, which is east-west trending right near in Batangan. when you correlate these with the petrography and the structure, you can see that the early parts, these are the early fabrics, these are overprinted, and then by these very high temperature assemblages, you have cordierite, then rimming garnet, which we correlate with the extension, which was possibly causing decompression in these areas. And then when you look at the structures here, you can see that there is some interference between grain boundary migration in quartz and feldspar, and then even lower grade structures, structural fabrics, which actually tell you an overprinting of the structures here. So summary is that you have the Glassman Hill structures actually deflected across a line which roughly corresponds to the coastline here, which we think corresponds to the D3 extensional shear zone trace, which we are trying to verify through the samples when they arrive. And then if you look at what Golinsky had actually published earlier, and you look at the aeromagnetic anomalies they've actually shown from this area. So one very prominent set of aeromagnetic anomalies seems to actually correspond with this line of the shear zones that we can observe here. So we think that the extensional fabric is actually supported probably by what we see in the basement, and this actually relates to the evidence of post-UHT deformation in the Glassman Hills. We have a reorientation of earlier structural fabrics. We think that there is extensional deformation, and we're seeing that the structural metamorphism do appear to resemble what we see in the northern eastern Ghats province. So what we're doing is an ongoing study to understand what this nature of this late event is like, and if it can truly be correlated with the extension that we've documented in the Eastern Ghats in India. So this is Dev Samriddhi during the 35th Indian scientific expedition, and this is Chandru during the 41st. We've had a lot of support from NCPR Goa, which facilitated the Antarctic research there. And well, thanks very much, and sorry for actually hurrying through the end. I think I mistimed myself.
Yeah, thank you, Savil. It's 10 minutes is not very long, is it?
No, sorry for that. Yeah.
No problem. Could you unshare your screen, please, and we'll move on. So our next speaker, thank you. Mohammed Sadiq, welcome.
So
Hi, thank you, Jacqueline.
Hello, Mohammed.
I'm trying to unshare.
Should be available to you now, I think.
Yes. Hi,
Yes.
am I audible, and can you see my screen?
I can see that. Yep. If you just pop it in presentation mode.
Yes.
Yeah.
Is it okay now?
Yeah, that's perfect. Thank you.
Yeah. Hi, everyone. I'm Mohammed Sadiq. I'm a geologist in Geological Survey of India, and I'm going to present the petrogenesis of new Proterozoic Cambrian granitoids of Frisbee area, East Antarctica. Now, moving on to the study area, Frisbee extends from West Forehead in the east to the Embry Ice Shelf in the west for a distance of about 500 kilometers along the coast. And the area is represented by the interleaved sequence of granite gneisses, metasedimentary rock, and subordinate amount of mafic granulite. This entire sequence is included by the different Cambrian granitoids. These Cambrian granitoids occur as discrete bodies, bands, stalks, lenses, and marking the last phase of igneous activity in this basin. Moreover, these granites are variously named as progress, Dolkoi, Amandabi, ending up on the basis of the area where they are exposed. So this is an ongoing study, and the work was just started in Jan and Feb this year. And during this year, we could study the different granitoids of Frisbee, and they are mainly garnet biotite granite, amphibole biotite granite, and amphibole biotite ferrite granites. This is how they appear in the field. These granites are reddish orange to gray to dark gray in color, and also the rusty red in color at West Canadian Pneumatic. This is how the hand specimen looks like. Moreover, we do have some photographs of granite dikes and bodies from different areas of Frisbee, such as Dawson Bluff, Roar Group of Island, and Stevens Peninsula. Geological mapping of selected island were also carried out in order to understand the relationship between different phases of granites, as well as to understand the relationship with the host composite gneisses and the metasedimentary rock, and to understand the deformation pattern if there is any. As you can see, this map, the foliation in the host as well as in the granites are similar. Another map showing the intrusion of biotite granites into the metasedimentary rock. Here we do have the similar foliation, but it's recorded in the host rock, but we do have some different trends also. In this granite, this is from the Daczko Island, and we had identified different FMEs and MMEs that I will be discussing. Wherever we could see the contact in different parts of plasma and Pisbe area, it is very sharp, except at few places. We had also identified tongues and epiphyses and granites, including into the metasedimentary rocks of plasma in this area. Another photo showing the contact of biotite granite and metabarite. Okay, the table shows the different characteristics of different granitoids of Pisbe, mainly on the basis of the field work which we had just done during this year. Most of these granites contain FMEs and MMEs, which I will be discussing in the coming slides. It is interesting to know that the granites which are exposed in the eastern part of the Pisbe are deformed, and the granites which are exposed on the western part, on the west of the Bharati station and the Progress station, are basically undeformed. Okay, we had identified different textures at different places of plasma and in progress granite, and that is honeycomb-like garnet fast intergrowth nodules and feldspar cordierite biotectic intergrowth. And besides, we have also identified sedimenite in the progress granite, which indicate that the progress granite is typically an S-type granite. Now, coming to the magmagenesis part, we had identified different types of magmatic enclaves in Amanda Bay, Daczko, landing bluff granitoids of this bay, which indicates magma mixing and mingling in this area. And perhaps this, as far as my literature review is concerned, this is going to be the first report on the magma hybridization in Pisbe granitoids. So we had identified different shapes of FMEs from the and MMEs, as well as the xenocrys from the Daczko granite. And these FMEs basically represent the globules of resident magma that was trapped into the crystal bush in upper part of the magma chamber. And the rounded and oval shape may be due to the both initial physical properties and the magmatic movement. The ellipsoidal MMEs can also be due to the deformation and erosion during the magma ascent and emplacement, and not necessarily due to the solid state deformation. We had also observed different types of and shapes and sizes of mafic magmatic enclaves from different granitoids of Pisbe. Most of these MMEs are porphyritic in nature. The porphyritic nature, the curved margins and diffuse margins indicate the emplacement of mafic magma before the solidification of granitic magma. And it is very obvious that these key feldspar phenocrysts in these MMEs grew in a stirred coval magma. These are basically produced by the different kinematics of interacting felsic and mafic magma. Okay, we had tried to identify the MMEs or FMEs in the progress granite, but we could not find any. However, we could see the rare biotite aggregates, and which may not be produced by the magma mixing or mingling. However, it can also be produced by the back reaction of peritectic garnet with the granitic melt as shown here. However, we could see many metasedimentary rock xenoliths of different sizes into the progress granite, as you can see in this picture. So these range in few centimeters to up to several meters in size. These photomicrographs showing the mixing texture. So we have the xenocrys, poikitic plagiocrys xenocrys showing the resolved margin and surrounded by the undercooled phases. We have the sea plagiocrys formed by the mixing of basic and acidic magma and subsequent resorption or of the feldspar. We do have the poikitic K feldspar as well as the plagiocrys, having inclusions of plage or key feldspar, biotite, and perhaps the sphen also and apatite. We also could get the titanite plagiocrys oxide, which is produced by the magma mixing and the subsequent back injection of felsic magma into the mafic system. So all these textures, along with the mixed apatite morphology, which we could observe, indicate magma mixing. The preliminary data, thermobarometry data, suggest the crystallization of granite at West Kannada and Nunatak at 760 degrees Celsius and 7.7 kbar pressure, and the formation of perthite at around 515 degrees Celsius at 5.5 kbar pressure. The prehistoric granitoids are quartz, monzonite, cyanide-to-monzogranite, and granite in composition as per the IUGS classification. And the geochemically, the progress granite is calcareous, meta-aluminous to para-aluminous in nature and plots within synchrosmal to volcanic arc setting. And it is, as I said, the progress granite is typically an S-type granite. This is a very preliminary data. We are yet to receive the samples. So far we could get the data from a granite dike cutting across the metasedimentary rock in Boston Bluff area and a dike syntectonic to the West Virgin folding in McLeod Island, Grassman Hills. And these are giving us an ages of 520 and 554 million years, indicating their emplacement during the Panopticon activity. The wide range of ages reported by various workers from the first bay indicates the a prolonged and protracted magmatic activity in this area. The map shows the configuration of India, Antarctica, and Australia during the Gondwana. And the star mark showing the location of the Panopticon granitoids. Some of the granitoids were dated by Jackie in her paper in 2017. So what I mean to say is that so the data, what we have generated and the data already published by various workers as shown here, indicate that the granites which are available in the Shillong or Assam Meghalaya Plateau or Shillong Plateau and the Brisbane, Antarctica and Australia and Yukon complex and the Batavia and all are of similar age and shows similar affinity. As you can see in this table, I had compiled the ages of Brisbane granitoids and the Meghalaya granitoid. These are falling in the same age bracket and have similar characteristics. Even we do have the fire bearing granite from the Brisbane from Munrokan Mountains, and we could find the fire granite from the Kirang Buton and from Meghalaya. So this indicates a widespread magmatism during the Gondwana assembly. Summing up, okay, the Brisbane granitoids are syn to post-orogenic granitoids, which show S, I, and E type affinity, and most of these granitoids contain magmatic enclaves, and some do contain FMEs. So the presence of MMEs, FMEs, and the mixing textures and the zigzag nothite profile from the piezochroids indicate magma hybridization in these granitoids. Besides the current data as well as the data generated by the previous workers indicate protracted, widespread, and multi-stage magmatism in different parts of India, Antarctica, and Australia during the formation of Gondwana supercontinent. This is a very preliminary study, and we are going to compare in the coming future. We are going to compare the geochemistry and going to generate more EAST data. Thank you. Thanks, John.
Thank you, Mohammed. That's great. So we've come to the end of our second block now. So we've got another Q&A session. Nathan, are you there?
Yeah, sorry.
That's okay.
Typing my question into the chat. It's a bit frustrating that we can't put it into the Q&A.
Yeah.
So we do have a little bit of time, probably about 5 minutes before people probably want to run for a quick break before our next session. There are some questions in the chat that both Jackie and I have put in there because we can't type into the Q&A. If we work through those quickly in order of speaker, the first one was from both Jackie and I think on a related topic, and Alexander responded to Jackie saying he's working on a manuscript on the topic of where the boundary between Indo-Antarctica and Australia-Antarctica might be based on the new data. And so I think we can all look forward to that paper. The next speaker, Nikita, there was a question in the Q&A asking whether the Charnokites were igneous. Do you have a quick answer for that, Nikita?
Yes, so I have answered to Laura in the chat. So, and then I answer again. So we have modeled the thermodynamic evolution of this orthogenesis.
Sorry, Nikita, we can't hear you. So perhaps you could just type it in the chat and we can we can read your answer from there. Thanks.
Yeah, thanks, Nikita. Sorry for the audio problems. We might move on then to the next speaker. Which
Sorry. So I typed in the chat the answer to Laura. So we
Okay, I'll ask Laura to copy that message to everybody. She can cut and paste it to everybody. When you type into the chat, there's a to line, and you might have just typed it to Laura only. So I'll get Laura to copy and paste it for us.
I'll have a look. Hang on.
All right. So Bal, I had a quick question for you, which was around the relationship between the Mahandi Graben, the failed Lambert Rift. Do you have a comment on that?
Yeah, I did type it into the box actually, but
Okay.
there's it's fairly detailed. The first one is that I don't think it's the failed rift, because the Mahanadi rift actually is around, it's Gondwana sediment, so it's around 300 MA. And the rifting between India and Antarctica is about 140 MA, so it's actually much later. So I don't think they're related, but it could be following an old plane of weakness. The second thing about your melt present deformation, D1 and D2 in our area is, yes, it was definitely supersolidus, and it was operating in the presence of melt. The extension and the later strike slip deformation, much lower grade, no melt, subsolidus.
Thank you very much. I can now see you're in the chat as well. It went to the host and panelists rather to everybody. I'll ask Laura if she can copy that one as well into the chat for everybody, so that people can read the answer as well. The last question I had was for the final speaker, whether the whether the granitoids were syntectonic, and what that said about the activity in the host rocks, whether they were deforming at the time of most of these granitoid intrusions.
Hi, am I audible?
You are, yes.
Yeah, I had replied in the chat box, and basically we do have, like I said, S-type and A-type granite. S-type granite are basically produced by the partial melting product of the metasedimentary rock in the area, and we could find the many evidences for that. And these, particularly the S-types, are deformed. Thank you.
Thank you very much. There aren't any other questions in the Q&A, and I can't see anyone with a hand up. And so I think that's possibly all the questions for this session. Thanks for Jacqueline and Laura for typing in those or copying in those answers to some of those questions into the chat for everyone. We might take this time to have a break. Jackie, do you want to announce about the movement to the next session?
Yeah, thanks, Nathan. So we've kept on time. So thanks to all our presenters in this first session. That's fantastic. We have our second session coming right up on the hour. IT have told me that we're staying on this Zoom call rather than switching to a different Zoom call, and I hope I've interpreted that correctly. So we'll be back here at UTC time 7 o'clock, so in 7 minutes. So I think it's a good time to have a quick break and get your drink of choice depending on what time it is in your time zone, and we'll see you back here hopefully on the same Zoom link in about 5 minutes for the next session.
Thanks, Jackie.
Thank you. IT, could you just confirm that that's what we're doing? We're staying with this Zoom session. I can see there's another Zoom session open, but I just want to confirm that we're staying on this one. Anyone from IT there? I think we're staying on this session, so we'll see you in 5. hopefully we can get started, and I'll have a chat with IT about that, Geoff. Thanks for reminding me.
Thanks.
I think that's everyone now who's speaking.
Okay. Okay, shall we get started then? Yep. So welcome back everyone. I think most people were probably in the previous session, but for those who aren't, welcome. And same as the previous session, we're going to have 2 groups of 4 speakers, each giving 10-minute presentations, and we'll hold questions until the end. So if you have any questions, pop them in the chat and we'll be able to discuss them in the Q&A session at the end of the 4 speakers. So I think if everyone's ready to go, the first person we have presenting is Ragram.
Yes, Ragram.
Yep, okay. Can you share your screen, please?
Yes. Is my screen visible?
Not yet.
Yeah, is it so?
Yep, so if you just pop it in presenter mode. Cool. I think.
Yeah. Just a little.
Yeah.
Yeah.
Great. Thanks.
Okay, so a warm welcome to everyone. I'll be presenting my preliminary study about metamorphism and migmatization in Schumacher oasis, and we'll be looking at this process through the purview of distribution of trace elements, especially in garnets. So just for a brief introduction, Schumacher oasis is a coastal nunatak in the central Dorning moorland. It is generally considered as an extension of the East African orogeny, extending and probably the extension of a Lurio belt into Antarctica. So this is the general geology of Schumacher oasis. So there are a lot of rock types here, but it is dominated by the metasedimentary packages, and metapelites and metagravax are quite common here. And there are 2 strong deformations here, 2 compressive regimes that we can see that I've marked on the map. So one is east-west, which has been refoliated or redeformed by a later deformation. And this F2 deformation or D2 deformation has resulted in predominant migmatization, and evidences of that are quite common in the field. So the deformational structures are spectacularly preserved, and we can see them in Schumacher oasis, both F2 and F3. The F1 is harder to trace, and generally we could not find it in the field, but it is recorded in literature. So the later folds are considered as F2 or D2. Okay, so as migmatization happens, there's a lot of generation of melts and leucosomes especially. So the entire process is preserved in Schumacher oasis, and we can see formation of layer parallel leucosomes which flow along axial planes, which cut across the folds and flow along axial planes, and then become discordant leucosomes, and many times turn into agmatites, preserving rotated and disrupted melanosomes or blocks of the protolith. In places, you can actually see the leucosomes flowing and disrupting the nose of the fold under compressive stress, as shown here. And with progression, if we follow Michael Brown's classification, then it will, from your metapelitic parent, we can see it changing to metatexite, then to a nebulitic or fleck diatexite, and finally forming layer parallel leucosomes, which are observed in mesoscopic scales in Schumacher oasis. Not just megascopic, but in mesoscopic scales, you can see leucocratic segregations with formation of peritectic garnets. And these peritectic garnets sometimes form large segregations, which can be noted. If we go about to the metamorphic history of this area in the process of migmatization, we see that it is a clockwise path and there's a sharp decrease in temperature, almost akin to an isobaric cooling. And this sharp decrease in isobaric cooling, we consider it basically the removal of the melt from the system, which has led to this rapid cooling. And the majority production of the melt is through muscovite dehydration and biotite dehydration. The PT estimates for the different units in the migmatic rock can be seen here. So from the parent protolith all the way up to generation of leucosomes, the different temperatures are recorded. The highest temperature recorded was 815 through TIN quartz using laser ablation. And the pressures are greater than 7 kilobar. These conditions of 800 degrees Celsius and at 7 kilobars are also noted in other places, like Carson noted this in 1997 in Larsemann Hills. So this is a common process that is occurring in at least the coastal land exposures of Antarctica. Within the garnet itself occurs both as selvages, especially in the metapelites and the protoliths, and going forward into the metatexites, they form peritectic garnets, and some of them are residual garnets from the parent. And along melt stringers, which can be segregated separately and noticed, especially in thin sections, you can see formation of peritectic garnets reacting with the melt. These garnets grow with the flowage of the melt and sometimes form extremely large porphyroblasts or poikiloblasts. Here you can see a large poikiloblast, which is a backscattered image of a poikiloblast with laser ablation tracks. We have basically tried to quantify the trace element compositions in garnets as they grow. And this is an elemental map of yttrium generated by microprobe, which does not show much variation, but the laser ablation data shows considerable variation. So if we just consider some key elements, we can see variation of from the protolith all the way up to the leucosome. Certain elements show a rapidly increasing trend and some others show a decreasing trend. Yttrium, for example, is proportionate to the temperature. So the presence of high concentration of yttrium in leucosome garnets, which are basically peritectic in origin, basically represents either resorption of monocyte and accommodation of that yttrium in the garnet itself, and probably forming at a lower temperature than the actual metamorphism that that was responsible for the melt generation. Even in chondrite normalized plots, we can see considerable variation in the composition of garnet, and these variations tend to suggest that there is the equilibrium has not been reached between the melt and the residue, and possibly further studies, especially elemental mapping through laser ablation and then quantification through partitioning studies, we'll be able to give a better insight into what exactly is happening. Now, if we try to constrain the ages, we get older ages for relict domains in monocytes. These are all chemical dates through microprobe, and these older ages of 800 or 750 have not been widely reported, at least from this Schumacher oasis. Most of it, the original you can say orogeny is considered to be Grenvillian, and the later Pan-African and the 620 MA East African orogeny is widely known, but the preservation of older relics raises question as to when exactly this migmatization process initiated, and whether it is simply a single stage metamorphism and migmatization of the metapelitic assemblage during the East African orogeny, or there are precursor orogenies, or the process itself was staggered in some way. So you can see further domains. This is a relict monocyte with 700 MAH, 770 MAH, and you have new monocytes growing on it during migmatization processes. These are from the leucosomes.
1 minute, please.
Okay. So basically, going to the summary, we can say the melt generation happened at high temperatures greater than 800 degrees Celsius under strong compressive regime, possibly by biotite dehydration. The lower PT conditions in the leucosome are the result by the garnets in the leucosomes absorb a lot more yttrium than in the metabolites. And the quantification and elemental mapping are the next steps, and we intend to do that through laser ablations and possibly do thermodynamic modeling and precisely constrain the entire process in this region. Thank you.
Thanks so much. That was really good. I think we'll move on to the next talk. So anyone who has any questions, again, pop them in the chat. So the next speaker is Roseanne Malik. Is she online?
No, I haven't been able to find that person. Are they in the attendees? Let's move on to the third speaker. And if Rosen appears, they could put their hand up for us.
Okay, well, the third speaker is Geoff Grantham, and I think he was hoping to play a recording, which may be IT. Have you got the recording of Geoff's talk?
No, ma'am. If you could just put your attention to the chat, please.
Sorry, Laura, IT have replied to me directly, which you can't see. So, Geoff, you're online. Unfortunately, your video link has expired and can't be downloaded. Is there another way we could present your talk today, or?
I'll give it a bash now, Jackie.
Okay, thanks so much.
If I'm up now.
Well, why don't we go to the fourth speaker and then give Geoff 10 minutes to try to get a new link to IT and see if in 10 minutes they can solve it, and if not, we'll try his talk at the end.
I can probably just do it online, Nathan.
Okay.
If it's
Yep,
if I can see everybody, I can just try and run it from here.
Okay.
Why don't you try sharing your screen, Geoff, and we'll see how we go.
I'm sharing screen now. Does anybody see it?
Nope.
Not yet, but there has been a little bit of a delay.
Sorry, just let me get back to. Sorry, I forgot to share it.
It's coming through now.
Cool.
That's it. Yeah, we just pop it in full screen mode and we can see your slides.
Okay, shall I get going?
Thanks, Geoff.
Thanks.
Okay, so he's going to talk about the chemistry age of granitic gneisses from Western Sphaerophylla. I just want to acknowledge my co-workers and also the organizations that are involved, particularly National Research Foundation for funding. And we'll move on to start the talk.
Sorry. Oh, yeah. Presenter mode, Geoff.
Um,
Can you make it full screen?
well, I have done, but it's full screen on my system.
It's okay. We can see the majority of the slide, Geoff. We can also see the side panel with slides 1 to 7 and thumbnails, but just continue. We can see it.
Okay. Okay, so the area we're looking at is down here in the sort of western end of basically the Kunga orogeny, which stretches in Antarctica on towards the western end between Enderby Land and the Gruner-Hogner Craton. So the area we'll be looking at, I'll show in more detail in the next slide down over here in the edge of the Kalahari or the Gruner-Hogner Craton. Okay, this is a more regional setting image. You have the Richer Flyer supergroup overlying the Gruner-Hogner Craton in this area, which is overlain by the Anandog-Stepani granite, which is an age of about 3.1 billion years. The study area we're looking at is over here, shown as a little rectangular area, and it's located in the moor terrain, which typically has 1140 to 1,000 million year old gneisses and granites, and is overprinted by the Kunga orogeny. I'll also be talking about the Borg massive, its suite later, which is on Craton, and also the Coen-Vegan area, just to indicate where they are for later purposes. Structurally, the rocks to the east overlie those in the west. Basically, they form part of the East African orogeny, and they overlie the moored terrain structurally. This is just a geological map of the granites that we're going to be looking at. There's a Util-Rora granite and Ruhr-Kulten and Brekarista. Util-Rora granite shown over here in pink, and Brekarista granite shown over here in two separate outcrops shown in red. And then the Ruhr-Kulten granite, again shown in this little pink area over here. The host gneisses are basically TTG, gneisses in green, and banded supercrustal gneisses in brown. Some field photographs of the different granite sheets. The Ruhr-Kulten granite forms a north dipping sheet, about 150 meters thick, and is basically medium grained, equigranular, very similar in appearance to Util-Rora granite, which also forms a south dipping sheet. And in this photograph,
sorry, Geoff, to interrupt. We're not seeing your slides progress. We're on slide 2.
okay, I'm not sure what the problem with the link is.
Yeah, we're seeing your screen, but I think it's just the way in the mode that it's in. It's not progressing to the next slide.
Yeah.
I understand.
Are you using dual screen?
Can you reshare, Geoff, and just choose the PowerPoint again?
I'll try that. That's sharing it.
We'll just give it a second to catch up with us. It's a bit slow sharing. Now it's coming through. Yeah, now it's working. Continue.
Okay, so the Util-Rora granite also forming a sheet 100 meters thick approximately, overlying the TTG gneisses in this area and overlain by the banded gneisses. And then moving to Brekarista granite, one can see field appearance is very different. It's porphyroclastic with a strong rodding of the porphyroclasts. Brekarista granite is also cut by many felsic and mafic veins, and we'll be showing some geochronology from one of those felsic veins. Doesn't seem to want to move.
Sometimes the arrows or clicking on the screen sometimes works too. The arrows.
Okay.
No, we're not
Okay,
getting,
there we are.
there we go. Yeah, perfect.
Okay, just looking at the mineralogy of the granites, we have the Util-Rora granite at the top. Mineralogy comprising hornblende, biotite, allanite, titanite, and garnet. And that's pretty much the same as the Ruhr-Kulten granite, except Ruhr-Kulten does not have any titanite. And then moving to the Brekarista granite, it's basically biotite, analyte, and titanite. And then the diuretic vein, which we'll be talking about briefly in terms of geochronology, it's biotite, hornblende, epidote, and titanite. Okay, looking at the geochemistry, as one might expect, they're all typically granitic in the QAP diagram, the O'Connor feldspar diagram. Some samples plotting as quartz monzonite, but typically granitic. The same in the TAS diagram, total alkali silica diagram. And we see here that they are both, all the granites straddle the boundary between metaluminous and pyroluminous granites. Using the frost and frost diagram, they all typically plot as A-type in composition. Moving on to the next diagram, looking at A-type discrimination diagrams after Whalen, one can see that all the granites again plot typically as A-type granites. If we look at the rare earth distribution patterns, the Ruhr-Kulten and Util-Rora granites are typically have very steep rare earth patterns, negative europium anomalies, actually quite rare earth enriched. You can see here chondrite normalized values up to about 600 times chondrite. The Brekarista granite, in contrast, has flat rare earth element patterns, also with a weak negative europium anomaly. The granites do, in other variation diagrams, have very distinct chemistry. We can see here niobium versus titanium. So they are fingerprinted chemically as being distinct. Using the Pierce discrimination diagrams, one can see that the Ruhr-Culton granite plots largely as a volcanic arc type granite, whereas the other two are typically within plate granite type compositions. When you look at the zircons that we've analyzed, this sample here is actually from a dioritic vein which intrudes the Breakup granite. One can see the zircons are very small, fairly homogeneous with very small sort of later metamorphic rims, which are too small to analyze. The zircons themselves are basically almost analytical spot size. If we look at the Breakup granite, one can see far bigger zircons with a lot of oscillatory zoning, but no metamorphic overprint rims. Moving on to the other granites, the Util granite and the Ruhr-Culton granite. Zircons are very similar, of having these fairly homogeneous interiors with slight metamorphic overgrowth, which were too small to analyze. Some grains showing a bit of oscillatory zoning typical of igneous crystallization. When we get to the analytical results, there were two unexpected results. The first was that the Breakup granite turns out to be Archean in age. We had suspected that there was a basement, Archean age basement to the Moor terrain previously from radiogenic isotope studies, and so this is the first exposure of Archean granite we found in the Moor belt. The dioritic vein which intrudes the Breakup granite we thought would be about 520, but it turns out it's age of 1119 and probably very similar to the tonalitic gneisses which form the basement to the area besides the Archean basement. The age data for the other two granites, Ruhr-Culton and Util granites, near identical ages, 1083, 1085. Low intercept ages are 655, but the error is so large that we don't necessarily think it has any significance. Moving on to the radiogenic isotope data, the two images we've got, this is showing all the data on a larger scale, and this is basically a blown, enlarged area of this part of this diagram. The rock units we're looking at, the granites themselves are shown here in green and red, and the other data from the Kernvegan in the south is shown over here. You can see it's a lot more juvenile, and that's in contrast to the basement gneisses in Spherophila shown over here in these sort of brown triangles. The Breakup granite with the Archean age, one can see that it plots part of a broad sort of Archean array with these yellow dot data coming from the Onondaga-Stepani granite. If we look onto what the data probably tell us is that the Ruhr-Culton and Util granites do not appear to be derived from partial melting of the basement gneisses, but they appear to be very similar to the Borg-Massivette suite, which is a large igneous province basic intrusion system correlated with the Mkondo large igneous province in southern Africa. Moving on to ethnium neodymium age diagram. Firstly, from the whole rock data, again, the same pattern is shown with Kernvegan granites being far more juvenile than granites in Spherophila of the same age, which plot identically with the Borg-Massivette suite and appear to be unrelated to the basement gneisses in Spherophila. The Breakup granite, again, one suggests with depleted mantle ages around about 3.1 billion years and possibly derived from partial melting of the older Archean gneisses. The same pattern is shown, but with slightly older model ages coming out from lutetium hafnium analyses of the zircons that were actually analyzed for the age dating. And again, one can see that they have a depleted mantle age around about 2 billion, but very distinct from the Breakup granite shown over here. Okay, just moving on to conclusions. So we have newly identified Archean age Breakup granite representing an Archean floor to the 1140 million-year-old Moor terrain. And we have this approximately 1080 million-year-old Ruhr-Culton and Ruhr-Culton and Util granites They don't appear to have been derived from local partial melting of the TTG gneisses, but have neodymium strontium characteristics comparable to the on-craton Borg-Bassavet suite, which is correlated with the Mkoda large igneous province. And I don't normally like using discrimination diagrams, but in this case, a within plate granite A-type signature appears to fit these granites. Diuretic vein, inferred to be about 520 million years, has actually an age of 1104 million years, similar to the ages of TTG gneisses in the area. Anyway, thanks for listening.
Thanks, Geoff, and thanks for persevering. I
No
think
problem.
we still don't have the third speaker, as far as I can tell. So I think we'll move on to the fourth speaker, which is Yingchuan. He's going to be talking about the Haas Bluff granitic friction. Hughes Bluff, sorry.
Yes, I can. Thank you. I'm here. And I will share my screen.
Yep. Great.
Okay.
Yeah, all good.
Okay. Good afternoon, everyone. Today I will give a short talk about the pathogenesis of the Hughes Bluff granite plateau in the Antarctic mountains, Antarctic. This is my talk outline. First, we know that granite is the most abundant rock in the continental crust, which make our Earth very different from other solar system planets. So, from as we all know that the granite have many different types. So just like that, said that granite, that reflect that granite is a big problem. So as we know, the Antarctic mountains extend more than 300 kilometers. So it are great continental mountains, and in these mountains, we know that the granite harbor granite is belong to related with those organs is very widely distributed along these mountains. So this is our today's topic. About this, the granite, there are some problems, especially with rare reliable age for many areas. So this makes it very difficult to understand their evolution deeply. So today I will give I want to talk about the Hughes Bluff. This outcrop. This we can view it from here. So the very small is no more than 2 square kilometers. So it is large in the western terrains, and we know the North Victoria land have 3 different terrains. So this province that in the western terrains, it is the south part of the David Glacier, and this field character, it's in this other corpus we can see many glacier traces. This is a sea bike spoon, and in the field we can this thundercloud and this host phase magma, and it was introduced by the fine grained thundercloud. It's wind, and we can from their minerals and also chemical composition, we can say them they are belong to the planetary granite on the TS diagram, and also on the QAP diagram, they are light in the thundercloud fields. And this our stream by Urim and the late 8th, and we can find the magma phases still happened on 550, and the wind is about 510. But within the area limited, we can't distinguish them. But in the field, we can define their relative relationship. And also, we use the mineral. I don't know just before we can talk about their genetic type. I think we should to define to discuss to know this granite is fractionate or non-fractionate. Based on the minerals, for example, there are no lepidode, so just based on the mineral, we can define this granite. It stands for the original. There are no non-fractional. So also these figures also figure that our sample it belongs to the I-type granite. And also based on their chemical combination, we also can determine that the magma was mainly derived from the crust. And other process, for example, the magnesium effects and there can the hafnium research also tell us the magma may be from the basaltic lava crust, on some mantle minerals may be devoted to them. And the formal temperature and the pressure, I think it is high for our research program. The temperature for them may be higher than up to nearly 900, and under their pressure it may be nearly between the 0.8 and 1.5 jet. And just from there, the years and under their distribution patterns, and we can find the niobium and the titanium and the titanium, the duplicate, and this character refer to them. They may be from formed in the isolated arc setting, and use this technique discrete diagram. We can find the line in the volcanic volcanic arc field. So I think we can infer them reformed in the volcanic arc setting. So these are the third conclusion. The Halpin bluff granite protein is mainly composed of medium to coarse grained porphyric and fine-grained standard granite. And this product, and two is this product were implemented at about 515. This main magma phase, and this responds to those organisms. And also, Halpin bluff granite have a matrilinear character and igneous type granite affinity, and was derived from the potential melting of the basaltic lower crust, and with also some metal materials contributed to them. And the final conclusion is that this granite were formed in volcanic island arc environment. That's all. Thank you.
Thanks so much. So I guess we've probably got a little bit more time for Q&A. Anybody who has any questions, again, please put them in the chat. And Jackie will kick it off, I think.
Yeah, thanks, Laura. So just to make sure we don't have our other speaker here, I haven't spotted you so far. Roseanne Malik or any co-authors that want to present on behalf of the group? No? Okay, so yeah, we have some time for questions. So unfortunately, as panelists, we aren't able to access the Q&A to type in the questions. So Nathan and myself have added a few questions in there, which I can summarize. So Nathan has a question for Raghuram, speaker one. How important are the co-crystallizing minerals in influencing the trace element content of garnet? Do you know if there is a difference in trace element patterns if melt is an equilibrium phase or not? Have you done that sort of thought about that sort of angle?
Yeah, so yes, certainly the co-crystallizing minerals are quite important. There are orthopyroxenes and biotites co-crystallizing with garnet, especially in the leucosomes. And the first row transition elements tend to partition into the pyroxenes and biotites. We are still working the partition coefficients. So soon when we publish, we'll be able to publish the details. Whether, do you know if there is a difference in garnet trace element patterns if melt is in an equilibrium? I've not really thought about it, but I think I'm going to pay attention to whether what happens when it's in equilibrium.
Thank you.
Okay, thanks. And so there was a couple of questions for Geoff, and Geoff's responded to one of those in the chat, but there was another one from Nathan, I believe. I'll just find that one for Geoff. Is there, I guess, so when you say tectonic diagram, you mean like a model, Nathan, that you like, that you prefer, that takes the Kunga origin through this part of Antarctica? I'm sure Geoff has a nice answer for that one. Is the Kunga boundary or zone well constrained in this region? Geoff, yeah, feel free to pop on your microphone and answer that if you like. Or
yeah, no. Yep. I would love to respond to Nathan, but it's a very detailed, complex thing. It's a lot of debate. I'd like to actually talk to him later, just independently. It's obviously relates to the debate between the extent of the East African origin into Antarctica and the extent of the Kunga. The East African origin, as it has been defined, is basically an age of roughly, say, older than, say, roughly 550 to 600 million years, older than the Kunga, which is an overprint of the East African origin, in my view. But it's a pretty complicated thing. I've got a poster up, which partly looks at the way I'm starting to see things. But, I've got a lot of data that I've still got to try and publish. But I think I've got a very good, would love to talk to Nathan and tell him exactly, or give him an insight into the way I see things, which is, different to the way other people see it as well. But it's just too long to try and even type a chat here, and with no figures, it gets a bit difficult.
That'd be great. We'll have to have a special meeting on the Kunga.
I think so, Nathan.
Thanks, Jackie.
Thanks, folks.
One thing I would like to say is just, you know, if you look at the sector that we're looking at, which I think is Kunga, it's probably the best exposed in the sense of the ease of direct relationship or lack thereof with the adjacent Mozambican terrains. And it takes a complicated story to address those differences. But we've got probably the best interface to try and study it.
Sounds like an invitation, Nathan. Thank you, Geoff. So we have a question in the chat here for Yingchun. Are there examples of dated granitic plutons in the area where the zircon geochronology is very complex and difficult to interpret? Ones perhaps that you didn't present on, or all the samples relatively tightly constrained in age? Would you like to answer that live or in the chat?
Sorry, I fear I can't hear you clearly. And
Okay.
just for the zircon dating, I can't. I have no. I'm sorry, I have no clearly the picture for the zircon here. So. And you know, in this study, we just dating this proton and no other data we got and other proton we measured.
Okay. So you just concentrated on that pluton, and it was a very simple zircon story there.
Yes.
Okay.
So when you know this outcrop is just mainly the granite, no other type of rocks occurrence.
Okay. Thank you. And Laura has a follow-up question to that, if you care to answer, about how similar or different the granite that you investigated is to those along the Ross origin. Have you compared more widely in the region the geochemistry and age? Perhaps something you could come to in the chat if you have some thoughts on that. Dan, you have a question for Geoff. Would you like to ask that, or would you like me to ask that on your behalf?
Oh, I can go ahead. Good day, Geoff. Good to hear you again. Question, any thoughts on the source of your Archean xenocrysts at Brecarista?
Well, I was just about to type a response, but it's easier just to talk, Dan. Nice to see you. How are you doing?
Yeah, lovely, mate.
Anyway, at the look, if one looks at a ridge of the Brecarista granite, you've got the two exposures. And so they pretty much just exposed its surface. But if you go slightly to the south of the second southerly exposure, literally within a couple of 100 meters, we have what I've previously published as called the Dalmatian granite. Now that Dalmatian granite, if the snow was removed, you'd probably see it cutting across the Archean age Brecarista granite that we see. So to come to the source of the Archean xenocryst in the Dalmatian granite, to me it's local. It's very local. But what I want to take, I've got other published data from further east, where we're also getting Archean xenocrysts in these same Cambrian age granites. So I think at this stage there's a lot to suggest that the Archean basement to the Moor terrain extends far further east.
Okay, that's great. I suggest we get together on Zoom and have a look at that. That'll be great.
And it's not just the xenocrystic zircons, it's also reflected in the neodymium data as
good.
well.
Right, so it's under there. Fantastic, thank you.
Thanks, Dan. Any more questions? I haven't spotted any in the chat, but if you would like to speak and you're not a panelist, you can raise your hand and I'll try and figure out how to amplify you.
Jackie, we're only 10 minutes ahead of schedule. I guess it seems that most people are here for the session rather than popping in and out. I guess we could have a quick 5-minute break and then start 5 minutes early for the second half.
Yeah, so we have all our speakers here for the second part. So that sounds like a great idea. So why don't we take about a 5-minute break, and we could start the next component about 5 minutes early. So if we say we meet again at, I'm going to convert to UTC 7.
Just do it in 5 minutes time, it's fine.
Yeah, 7:53, 7:55, we'll start the next block of 4 talks. If you think of a question in the meantime, pop it in the chat or the Q&A, and we can come back to it in our final Q&A. Thanks everyone, we'll have a 5-minute break and see you again.
Welcome back, everyone.
Thanks.
That was 5 minutes, I think.
Yep.
Okay, so let's get started with the next 4 speakers. And next up is Charmaine Veerhart. So Charmaine, if you're online, can you share your screen, please?
Yes, hello. I'll try to share my screen. It's been a while since I've done this with Zoom, so I hope this works. Can you see my screen like this?
Not yet.
No, not yet.
Oh,
Okay.
yep.
Yes.
Yep, perfect.
Cool. All right. So, hi everyone. I am Charmaine. I'm a new PhD student at the University of Adelaide, and I will be talking about the research I've been doing over the past few months on some garnet-rich beach sands from South Australia that might give an insight into the geology of East Antarctica. So usually zircon uranium lead is used as a detrital geochronometer, but zircon is very resistant and can be recycled several times. It's also often biased against intermediate and felsic source rocks. So it often misses the recording of magma pour or metamorphic events. Instead, garnet can be used for provenance studies with metamorphic source rocks, and it can be used to investigate more immediate sources or unicycle events as well. Traditional methods on garnets rely often on chemical separation, which can be too time consuming for provenance studies because a lot of grains need to be dated in one go. So laser-based lutetium hafnium geochronology could provide a better alternative for detrital studies because laser spots can be placed directly on a bunch of garnets themselves. So I will showcase the potential of this method for detrital provenance studies using a case study I'm working on for my PhD. It's still pretty preliminary data set, and there's still a lot to uncover from the ages and the data I gathered so far. So for the method itself, the details are explained in Alex Simpson's paper in chemical geology, but essentially the method is laser-based. So the garnet grains can be targeted directly in the laser unit. And a big number of grains can be analyzed in one and the same laser session as well. A high spatial resolution can be achieved because the method also allows for dating different metamorphic growth zones in bigger garnets, for example. So the resulting ages are also pretty reliable, which I will show with the following example. So along the Fleurieu and Peninsula coasts, Fleurieu Peninsula and York Peninsula coasts in South Australia, there are a few concentrated garnet-rich heavy placer sands on the beaches that can be found, and they can be distinguished from their pink colors. because of the garnets in the sands. And it is believed that those sands were winnowed from glacial units that were deposited on South Australia by ice sheet flow in the Permian. And they are these bluish units. So the sample comes from Maiponga Beach, which lies in the catchment area, which comes from the Adelaide Hills. In the Adelaide Hills, there's the Maiponga Inlier, which is part of the Barossa complex, which contains pegmatites, which also contain garnets that can end up in the catchment. So these are the resulting lutetium-hafnium isochrons and radial plots. We're still deciding a bit on the best way to report detrital garnet ages because it's difficult to derive different populations from the isochrons itself, as you can see. It's pretty subjective on how you select the different grains for the different isochrons. I base the selection on the radial plot, but I think the radial plot would be a more or a safer alternative to reporting the data. But essentially, both the isochron and the radial plot show two main age populations of 560, around 560 and around 1,616 million years ago. So the older population could be correlated to the Barossa complex I talked about earlier, because a long-lived phase of metamorphism is recorded in the Maiponga Inlier, which starts at around 1630 million years ago, and which that correlates to the older population in our beach sand data set. But then the younger population of around 560 million years ago doesn't really correlate to local geology. And these ages relate to the case study I will talk about in the next slides. But the Maiponga beach sand sample kind of showcases the potential to use garnet lutetium-hafnium geochronology for detrital studies, as the ages seem reliable compared to between the isochrons and the radial plots, and the uncertainties are relatively small as well, even though the provenance isn't immediately clear from the data sets. So I'll talk about the case study I've been working on, and I'll be talking about two other samples from the Fleurieu Peninsula in South Australia, so Hallett Cove and Petrel Cove. They are also in the vicinity of these Permian glacial units, which is also known as the Trubridge Basin, from which these garnet grains are believed to have been derived. I did some zircon uranium lead dating on those samples as well, and the main populations are similar between the two samples. They range from 550 to 559, 570 million years, but they are remarkably lower than the lutetium-hafnium ages that we got for these beach sand samples, which I'll show in the next slide. So for Petrel Cove, the main age population was 615 million years, with a few minor age populations as well. But this sample clearly showcases how difficult it is to get a clear set isochron for one population, as there's a lot of overlap, and selecting them would be very subjective. So that's why I would suggest reporting the ages in the radial plot or something else instead, because there's still a lot of influence from low radiogenic grains that can also influence the different populations. So we're still working on the best way to report these lutetium-hafnium data sets. But when we compare Petrel Cove to Hallett Cove, the ages are kind of similar. The main population in Hallett Cove is 620 million years ago, and the minor populations are kind of similar within uncertainty as well. But still, it is quite a bit higher than the ages we got from the zircons. And also these ages cannot be directly correlated to the local geology of South Australia. So if the ages cannot be corrected to the local geology, then what could the potential provenance be of these grains? It is hypothesized that the grains come from these blue Permian glacial units that were deposited on South Australia due to the ice flow of the ice sheets in the Permian. The ice sheet flow was from southeast to northwest mainly. So instead, it is thought that the garnets could have been derived from Antarctica, where the same ages have been previously described along the East Antarctic margin. And South Australia was formerly part of the Australian Antarctic system within the Nuna, Rodinia, Gondwana supercontinent configuration as well. Another possible provenance region could be the South Tasman rise. When looking at the ice sheet flow and Gondwana configurations, the South Tasman rise lies southeast from South Australia in those reconstructions. So if that's the direction of the ice sheet flow, it's possible that the garnets could come from the South Tasman rise instead. But this region is only sparsely sampled at this point, so further research should be conducted. And then just some conclusion, sorry.
Thank you. Yeah, wrap up 1 minute, please.
Yep, I'll wrap up. So again, the advantages would be that it's very quick and you can get metamorphic ages on the metamorphic events that are quite reliable and have low uncertainties. And for future research, I'll be conducting more compositional data on the garnets and the other minerals and try to get some lutetium hafnium ages from the surrounding geology in South Australia and also from rocks from East Antarctica as well. And that was it. Thank you for listening. So I'll stop sharing. Yes.
Yeah, thank you.
Yeah, I haven't looked at the chat, sorry.
So we'll do chats, answer questions after this next block of talks.
Yeah.
So there is one in the chat, so maybe have a think about it.
Okay, cool.
Okay. So the next speaker is Maureen. I can see you online. So if you're ready to go, please share your screen.
Can you see the slide?
Yep, looks perfect.
Okay. Yeah, hello everyone. My name is Marian Lösing. I'm currently finishing my PhD at Kiel University. And this talk is going to be a little bit more geophysical rather than geological. I'm sorry for that. But I'm going to present the results of our project for which we used Australia to learn about the heat flow in the Wilkes Land region in East Antarctica. So geothermal heat flow is one of the most important but poorly understood boundary conditions for ice sheet modeling because it can affect the ice rheology and Bell's melting and sliding velocity, and therefore it can decouple the ice from the bedrock beneath it. And to quantify the heat flow, the thermal gradient over a certain depth interval is measured. And as shown in this figure, towards the interior of Antarctica, we only have very few direct estimates from ice boreholes, which are prone to large uncertainties due to unknown heat sources within the ice. And so in order to produce a continent-wide geothermal heat flow map, we need indirect methods based on geophysical data. And these maps that we have not only need to be well constrained, but also constrained by multiple sources of information, also in high resolution, in order to capture the spatial variability of heat flow that we can observe, for example, on other continents, and especially in regions of slow ice flow, localized elevated heat flow anomalies can lead to increased basal melting and the initiation of ice flow, as shown by the two studies here, for example. So Pittard and others used 120 milliwatts per square meter in a 25 by 25 kilometer region instead of the Morrissey flow model by Fox-Moller and others that has a resolution of a few hundred kilometers, and show that this results in differences in surface velocities of around 100%. And McCormick and others showed that the different heat flow maps that they are using vary in smoothness, all have a mean of 55 milliwatts per square meter, and all lead to higher basal melt rates than a uniform heat flow map of the same value. So in order to increase the spatial variability in Arctic heat flow maps, we need to consider the impact from geology, which is poorly unknown on the thick ice cover. And therefore we use geophysical data, so magnetics and gravity, based on airborne and satellite measurements, to jointly invert for susceptibility and density distributions within the crust. And this inversion approach is based on a coupling that reduces the variation of information between the inverted quantities by assuming that the magnetic and gravity anomalies originate from the same geological sources. And we focus on this area, so Wilkes Land and South Australia, because we assume that both are similar in terms of tectonics due to their connection in the Gondwana assembly. And also this allows us to use Australia as reference and to learn from it, because tectonics, geology, and heat flow are much better understood than in Antarctica. So here's a visual example of what the coupling in the inversion does. So if we have two variables and we plot them against each other, you can see in this upper diagram, we have a rather random distribution with no relationship. So we know something about the first parameter that's probably somewhere here. We don't have any information about what the other parameter could be. And in a histogram, we can measure the compactness along the different axes, which corresponds to the entropy, and which in turn tells us how high the variation of information is. So in this first example, we have low compactness and high variation of information. And in this lower diagram, we see a much more compact version with low entropies, and the information about one parameter constrains the outcome of the other. So during the inversion, in addition to reducing the misfit, one objective is also to reduce the variation of information. And in our case, the inversion leads to a certain relationship between susceptibility and density. And we do it for Australia and Antarctica. And this results in a unique combination of these parameters for different structures, which could facilitate the geological interpretation. And we can observe that the spatial distribution of these parameters, so susceptibility and density, is very similar, and that some structures align along already identified faults and tectonic provinces. And for example, we can identify the Albany-Fraser origin and the Musgrave origin, and also here the Nux Rift, which is with its affiliation to the Perth Basin in South Australia. Further, we can take a look at this depth profile, which is where we have additional information from a seismic survey. So we can observe a broad agreement between boundaries of inversion structures and major seismic reflectors, which supports the validity of the vertical extents of our results. Especially the large scale seismic provinces are captured well. And for example, the prominent Mundra-Bia shear zone that reaches from Australia into Antarctica is visible, and it plays a key role in understanding the transition from the supercontinent Colombia to Gondwana. It's characterized by sharp gravity gradients, and we can find it here aligned boundary of two structures, which separates the Madura province from the eastern Western Campana province. So now this quantitative and structurally similar information not only indicates connections across the two continents, but it's also really useful to extract information from Australia into Antarctica. And here we use it as input for machine learning, similar to some of our previous approaches. And we added to the inversion results the topography slope and regional Moho depth, and link this information to the in-situ heat flow estimates that we have on both continents, and build a prediction model. We split the data into 80% training and 20% test data. And as you can see, all these different inputs are contributing to almost the same amount to the prediction, which results in a model that is able to predict the training data with an almost 80% accuracy and the test data with about 60% accuracy. And regarding the large uncertainties for the ice profile measurements that I mentioned earlier, it's not our goal to get a one-to-one prediction, at least not for Antarctica. Yes?
1 minute, please.
Okay. Yeah. So most of the predictions are within plus minus 50 millivolts per square meter, which is the average of the uncertainty for Antarctic measurements. We perform a jackknifing, so we get average, minimum and maximum maps. And this is our final heat flow prediction with in-situ measurements. We see that in Australia, colder regions correlate with older cratons, such as the Yilgarn craton, and generally higher values can be found here in the Murray-Darling Basin. In Antarctica, we observe high values close to Lake Vostok, here at the Law Dome, where we expect, or where we observe increased ice mass loss, and in Ter Alali, which is connected to the Gala craton, where we also have high heat flow anomalies, possibly due to high heat production. Yeah, and in comparison to our older model, the new prediction has a high resolution of 15 kilometers due to the regional focus. And with this, we are able to capture more of the heat flow variability and hopefully in the future improve our understanding of subglacial conditions for ice sheet models. So yeah, to summarize, geothermal heat flow is crucial for ice sheet modeling, and recent heat flow maps are getting more similar and using statistical methods and multiple sources of information. But we still need higher resolutions to counteract a systematic or a possible systematic underestimation of basal melt rates. For this, we need to enhance the understanding of the Antarctic crustal architecture. So we did a joint inversion of crust for crustal density and susceptibility structures, and used statistical methods to predict high resolution heat flow for Wilkes Land, which is in good agreement with observations. Thank you, sir.
Thanks, Marie. And I think there's already a question in the chat, so if you can have a look at that and maybe answer that in the chat or answer it in the Q&A. And the next speaker, I think, is me. Yes, it's me. So I guess I'll share my screen. Is that working?
Yep, that's all good, Laura.
Cool. Okay, so I'm going to go back to sort of India, Antarctica, and the Prince Charles Mountains. So as we've heard, Antarctica has sort of three affinities: Australian Antarctica, Indian Antarctica, and African Antarctica. And there's a lot of debate about where the boundaries between those go. But then there's also some debate about where those pieces of crust fit in terms of supercontinent reconstructions. So the part of Antarctica I'm looking at, which is the Prince Charles Mountains and specifically the Rainer complex, it records metamorphism coeval with the formation of the Rodinia supercontinent. But there's quite a lot of debate about where it sits in the Rhodinian supercontinent. So some reconstructions put it over towards sort of as an isolated piece of crust, and other reconstructions put it as part of the main Rhodinian supercontinent. So the motivation for this work, which is still a work in progress, is trying to actually work out where the best place to put it is and how to fit it into these reconstructions. So the Prince Charles Mountains comprise several terrains with different protolith ages and slightly different metamorphic records as well. The southern Prince Charles Mountains comprise the Ruka terrain and the Lambert terrain, which have Archean to early Paleoproterozoic protolith ages. The Rainer complex and the Fisher complex have dominantly Mesoproterozoic protoliths, and they're relatively juvenile. Together, the Rainer complex and the Eastern Ghats, which is its conjugate in India, are thought to be about 2,000 kilometres across and 500 kilometres wide. So they're a pretty significant piece of crust to be incorporated into tectonic models, and they're a significant piece of crust to just be considered as a question mark. The history of the Rainer complex at the moment is proposed to be a series of outstepping arcs that formed on the extended margin of India. So it's thought to be about 400 million years of arc magmatism, which produced a series of relatively juvenile arcs. These eventually collided with East Antarctica, somewhere between 1000 and 900 MA, which resulted in granulite facies metamorphism, ultra-high temperature metamorphism in India, and a lot of magmatism. But we don't know very much about the protolith ages or the isotopic character of these outstepping arcs. And the Rainer complex, in addition, contains a lot of metasedimentary rock, but we don't have any constraints on the source of those metasedimentary rocks. So one way to test whether this outstepping arc model works is to look at detritus and see whether we have Antarctic detritus or potentially Indian detritus. Mount Lanyon, which is the focus of the rest of this talk, sits at the southernmost part of the Rainer arc, right at the margin between the Rainer arc and the Fisher arc. It contains peelite, calc-silicate, and mafic and felsic gneiss, together with Mount Meredith, which is the mountain next door. It was thought to contain an early granulite facies myelonitic thrust fabric, which predates the thrust fabric seen elsewhere in the northern Prince Charles Mountains. But this was all done before geochronology, so the age of that's not well understood. And again, we don't know anything really about the protolith ages or the isotopic character of rocks from Mount Lanyon. We do know something about the metamorphism, which is that it contains granulite facies mineral assemblages, so it's got a garnet rutile sillimanite bearing mineral assemblage. Rutile is quite uncommon in the northern Prince Charles Mountains, and it's slightly higher pressure than the metamorphic assemblages seen elsewhere. But then there's a secondary cordierite bearing mineral assemblage which overprints this, which replaces ilmenite replaces rutile and cordierite replaces garnet. In terms of geochronology, it looks like the high pressure event was early and formed around 1020 MA, and then the cordierite bearing assemblage corresponds in terms of timing and pressure and temperature conditions to the main Rainer event, which we see elsewhere in the northern Prince Charles Mountains. This is just a compilation of all the monazite and zircon ages from the northern Prince Charles Mountains and the Mawson Coast. And as we can see, the geochronology for the metamorphism at Mount Lanyon corresponds really well to fairly standard Rainer orogeny ages that we see elsewhere. The mafic gneiss at Mount Lanyon has a couple of different protolith ages. So one sample gives a protolith age of about 1350 with then some metamorphism and drawdown that corresponds in terms of age to the metamorphism we see with the monazite. And then there are two other samples that give ages of about 930. All of these have been metamorphosed and deformed. And again, 1300 to sort of 900 are really standard Rainer ages. They're pretty common in the northern Prince Charles Mountains, the East Amory Ice Shelf, and also the Fisher terrain. The granitic gneiss samples from Mount Lanyon are a little bit more interesting. So they give ages of about 1730. They're biotite granites and orthopyroxene granites, which have obviously been metamorphosed and deformed. And this age is a bit more confusing. So there are rare xenocristic zircons in younger magmatic rocks in the fissure terrain of around 1700-ish. There's also a leucosome from the Lambert terrain that's thought to be about 1700 million years old as well. But in terms of knowing what this means as a big scale or regional event, it's just not that clear at the moment. And then finally, there's metasedimentary rocks, so quartzites and metaphilites. We dated this quartzite, and this one was really interesting because it's actually got Archean to earliest Paleoproterozoic detrital zircon in it. And so the maximum depositional age of this rock is about 2100, and then it's got Archean detritus, which really is not known from the Rainer or fissure terrains at all. But it does correspond in terms of timing to magmatism and metamorphism in the Ruka and the Lambert terrains in the southern Prince Charles Mountains. In case you're wondering if it's just a localized single sample, Mount Meredith next door also contains detrital peaks around 2800 to 2500. So these were analysed prior to CL images of zircon, so the peaks are a bit smeary, but they do seem to correspond to the peaks that we see in the Mount Lanyon sample. Similarly, Mount Meredith and the fissure terrain both contain a detrital peak at 2100, which corresponds to the main peak that defines our maximum depositional age from Mount Lanyon. So it looks like these ages are at least reasonably common in this part of the sort of Rainer complex and southern northern Prince Charles Mountains. So just, I guess, the final thing is to then work out what this might mean. And it looks like Mount Lanyon might be a way of linking the northern Prince Charles Mountains and the southern Prince Charles Mountains. So Mount Lanyon and Mount Meredith look like they have a Paleoproterozoic history. They have sediments that were deposited in the Paleoproterozoic somewhere between 2100 and 1800. And these sediments look like they're sourcing detritus from the southern Prince Charles Mountains, Archean and early Paleoproterozoic rocks. But they do also have a pretty convincing Rainer age magmatic and metamorphic record. So they look like, in terms of the metamorphism, that they belong in the Rainer terrain. The fissure terrain, again, also has ages that correspond really well to what's known elsewhere in the Rainer complex, but it also has this older sedimentary detritus, which suggests that it has to be also potentially sourcing something from the southern Prince Charles Mountains. Or I guess alternatively, if the Rainer complex turns out to have a significant Paleoproterozoic component, then the fissure terrain could be sourcing recycled Paleoproterozoic detritus from the Rainer as well. So I don't really know the answer to this yet, but reconciling the southern Prince Charles Mountain ages in what's supposedly the Arc terrains is key to placing this part of Antarctica into tectonic models. So stay tuned, and we'll hopefully be collecting some more data which will help to unravel this story. Thank you. Okay, well, that's done. I guess we can move on to Dan Dunkley, who's the next speaker.
G'day, thank you, Laura. Let me just get my screen shared up here. Sorted. Okay, and let me know if you can see that okay.
Yep, just pop it in presenter mode. Yep, great.
That looks good. Okay, let's go. Thanks, everyone. It's good to see some faces that I haven't seen for a long time. Would be better to see you in person. I hope that can happen soon as well. Monica has asked me to present this work on her behalf and on behalf of the team, which includes people from Poland, Australia, Sweden, England, and it's a real international effort, something which is an ongoing effort that people involved in this project have been conducting in the last 10 years. In its current form, led by Monika Kuszak at the Polish Academy of Sciences. This is a joint Poland-Norwegian funded research program under our banner of Poles Together, where we are looking at early Earth remnants in both polar regions, north and south. The work I'm talking about today is looking at Eoarchean remnants in the Napier complex. So I'm not going to talk about geology or supercontinent correlations. I'm just going to talk about zircon. My apologies to those who'd rather listen to geophysics. But I would like to thank Chris Carson and Alex Post of Geoscience Australia for all their support and access to legacy samples from the Australian Antarctic expeditions, especially those conducted in the 1980s and 1970s, of which we are using as a sample base for this project. Now, a lot of talk during this session and the previous session about the work around Bunga Hills, where the Indo-Antarctic continent, if you like, and an Australian Antarctic continent have a juncture. We are a long way from the Bunga Hills here, where Monika and other members of the Polish Academy of Sciences have recently returned from the reopening of the Dąbrowski Polish Research Station after 40 years. But here we are right over the other side of Antarctica at the Napier complex, which is, as I'm sure all of you know, part of the Gondwana assembly around 600-500 MA and conjugate to Sri Lanka and India within that assembly. And that's about all I have to say about supercontinents, because what I want to talk about today is not the assemblies that go back even to the Archean age, but the remnants of materials that are present within this Archean remnant of the Indo-Antarctic continent that predate 3.6 GA. And they are rather rare. And in previous studies over the last few decades, they were only known at one locality, that is the Tula Mountains, and more specifically the West Tula Mountains. And there were just a few samples amongst a great variety of charnokites, endobites, and other high-grade rocks that are much younger, Archean, but only about 3.2 to 2.5 GA in terms of protolith and metamorphic ages. The older material, the stuff that's older than 3.6, is only found in mount zones at Gage Ridge. In that part, those ages have been known for many decades, but have been refined and further studied in the last few years. The teams in Russia have also discovered Eoarchean ages over in Kempland on the eastern side of the Napier complex at Acker Peaks. But the ages are only tentatively demonstrated in Belyatsky 2011. And this study will mostly talk about the results found at Acker Peaks with samples that were collected by Australian Antarctic expeditions back in the 70s. However, there has also been new discoveries in the last couple of years by members of our team. In between the two, about halfway in the eastern Tula Mountains, around Budd Peak and Mount Jewel, we also find 3.7 ages and also some 3.5, 3.6 ages, and maybe a sniff of metamorphism around that time as well. The important thing to realize here is these could be just tiny little cherries in a cherry pudding, but they could be indicating a larger extent of Eoarchean crust within a Neo-Archean metamorphic complex, the true extent of which remains to be demonstrated. So that's it for geology. Let's just talk about zircon. The zircons are somewhat hideous, as is commonly the case of zircon preserved in high-grade metamorphic rocks. And their interpretation is intrinsically ambiguous because you must not only rely on the age data, but the texture of mineral growth within these tiny crystals, which can be readily modified after stages of growth. So here we have two samples of particular significance because one, they present age data that spreads between the known metamorphic age in the Napier complex of 2.5 GA and about 3.7 GA. So this upper intercept age of 3.7 should be either the age of the protolith or the age of a metamorphism of a protolith. And here's the thing, these are mafic orthogneices. They have basaltic geochemistries, and in such, they are unique. We have not been able to see a demonstration of the existence of mafic protoliths that are definitely Eoarchean in the Napier complex before. It's probably common, but it's rather hard to date mafic orthogneices by zircon. Here we have a couple of examples where the protolith age of these mafic orthogneices must be 3.7 or older. The reason I put an ambiguity in here is because the textures that you find inside these zircons are such as are typical growing in mafic melts, but are also rather typical of zircon growing in high-grade metamorphic conditions. It's very hard to tell the difference between the two. So let's have a look at a trondhjemitic orthogneiss from the same sample set, collected in 1977. And this one's a trondhjemite, and it is rather more complicated. If you don't look too carefully at your data, you could just draw a line through this spread of data and pretend it's just a simple lower upper intercept array. But the statistics, the MSWD will tell you that there's something more going on. And in fact, the textures are more complicated. They do preserve oscillatory zoning as befits a granitoid or zircon growth in a magma that is granitic in composition, but there are clear evidence of modification of these original textures. Nathan, you'd like this stuff. This is all pretty hideous to most people, but it demonstrates that these zircons are recording more than one stage of growth and or modification. And the chemistry, the uranium contents, relative to uranium, thorium-uranium ratio, you can see that there are two groups, a type U, which is relatively low in thorium-uranium ratio, and that tends to be in rims and patches that replace other zircon. So we do have a metamorphic component over an igneous component, which should give us the protolith age. But it's complicated. SIMS data shows a great spread, which partly can be attributed to 2.5 metamorphism and the lead loss that causes, but also must be separated if there is any hope to define individual ages, because the spread cannot be just due to 2.5. Here I have separated, based on textural relationships and composition, into three groups that spread down to the lead disturbance point at 2.5. You can think of the middle age, 3778, as a minimum age for the protolith of this tonalite, with the possibility of xenocristic material going back to perhaps 3860, and a distinct low thorium uranium modification of zircon at 3.7 GA, typical of what we find in metamorphism. And that is unique because it is the first clear evidence of metamorphic zircon growing in the Eoarchean in the Napier complex. Jacqueline knows of some ages that are similar to this, slightly younger, that are found in the adjacent Rainer complex, but this is something that needs to be looked at more.
Dan, 1 more minute.
1 more minute, okay. The hafnium data is interesting because with split stream, we can tie lead ages to simultaneous hafnium lutetium isotope behavior. But what I think this demonstrates more than anything is that the lead ages that are meant to be synchronized with hafnium in complex zircons, in fact, do not, that they are almost always disturbed. And as you can see here, the hafnium behavior is fairly steady, whereas the lead behavior is variable. And therefore, if you try to use such ages in split stream to define your epsilon hafnium array, you may get a wrong interpretation. The lower plot plot D shows these shrimp ages calculated from upper intercepts applied to the hafnium data. And as you can see, they indicate chur-like growth of zircon. In other words, this is probably from new or unevolved crust, but there is slight negative values here and in the mafic stuff that is younger that suggest possible derivation from an older mafic crustal component, not a Hadean one, but certainly older than 3.8. And at that, I'll leave it to you. Here's some conclusions for you to ponder. Thanks very much.
Thanks, Dan.
Yep. Cool. So I think that's our last speaker. So I'll leave it to you, Jackie, to do the chat question answer.
Thanks, Laura. Yeah, thanks to all our speakers in this session, or this half of this second session. So we've got some time for questions. Some of the questions have been answered in the Q&A already, so that's great. They disappear pretty fast once they're answered. So have a look in there because there's some ongoing discussion. So that's really good. So I'll just focus first on the ones that are in the chat because they haven't been answered yet. So there's a question here for Charmaine. Well, there's a series of questions. Charmaine, do you feel like answering online, or are you happy to chat about those questions from Nathan?
I don't think I answered all the questions yet, but I can elaborate a bit more by speaking, I guess. To
I
get
see
my
you
idea across. Yeah, I just replied at the end of Daniel's presentation.
For everyone, because not everyone.
I've done that, Jackie.
Oh, thanks.
All right.
Sure. Would you like to elaborate a little bit, Charmaine?
Oh, okay. It wasn't visible for everyone. Okay, cool. The first thing, well, I haven't seen the method applied to very young ages or very young garnets so far, so I'm not sure how young the ages can be for it to be still very accurate, I have to admit. So hopefully more research will be done on that aspect. Maybe some younger samples can be dated in the future as well. So when comparing the next question, so for the garnet bearing metamorphic rocks, it is generally a bit more easy to infer the ages because you can target several areas in the garnets in the rock itself. You can target either the rim or the core. So when you know what areas in the garnets you targeted in the actual rock sample, the isochrons will be more clear and often only one real isochron age can be derived. Whereas in the sand samples, we don't really know what part of the garnets we're targeting because they're weathered. They could come from a core, from a rock in a source region, they could be a rim. So it's more difficult to interpret the ages as well as the multiple populations that are present in our samples. And then, for microstructures, the grains should be pretty homogeneous, I think, and as large as possible because they require a pretty large spot size as well. So it's best to avoid inclusions as well as see if it's possible to distinguish zonation before you actually analyze the grains themselves. I think that's most question for me.
Thanks, Charmaine. I was just reflecting on Dan's talk and I wonder, you could apply it to these really old rocks. Like, how old do you think this technique could go back? Is there an opportunity for looking at some of this really old material in Antarctica using this method?
I think it's definitely something that should be explored. So hopefully that's something I can still do further in my PhD as well when I'm looking at actual rocks from Antarctica. Maybe I can try to date some of those very old rocks and see how accurate the method still is compared to the published data.
Thank you.
Yep.
I wonder if the garnet might do better than the zircon, Jackie, at dating the metamorphism.
Yeah.
Potentially, maybe.
That would depend on how much has happened to it after that.
Yeah, yeah.
So, mhm.
Find
Yeah,
us garnet in a
closure-
zircon and we can do it.
The closure temperature is a bit still not that well known. But the main constraint, I think, is if you've got lots of zircon, then you don't necessarily have enough lutetium in the garnet.
Yeah, I think that's one of the problems as well, because it gets incorporated in the zircon grains.
Right.
But if they're really ancient, there'd be enough radiogenic hafnium even from a small amount of lutetium, so it might work.
Yeah.
Okay, thanks, folks. So there's been quite a bit of discussion about Maureen's talk. So thanks, Maureen. That was really interesting. And Maureen's posted some comments to Alan's questions in the Q&A. I had an extra question, if I could, Maureen. I noticed that you had quite a high heat flow south of Lord Dome, just the southern part of Lord Dome. Do you have any ideas about what might be driving that from your analysis?
Yeah, so at Lodom we have a quite high heat flow measurement, and we also got quite high susceptibility features from the inversion. So these lead to the high prediction there. And actually close to this region, geophysical data was interpreted as possible intrusions, which are similar to central southern Australian granitoids. So this might be something that leads to this high heat flow.
Yeah, that's interesting. I was also wondering if, whether the crustal thickness there is substantially different to the crust either side, whether that's part of a rift structure. I'm not sure.
I think in this case, the susceptibility was the main driver for this. Yeah.
Okay. Yeah, thanks. Did you want to comment on the discussion you're having with Alan, or?
Yeah, so maybe for everyone, so we used the topography slopes instead of the total heights, just to make the two continents comparable. So because Antarctica is slightly subsided due to the ice load. And yeah, topography is an important influence for heat flow because it can lead to defocusing and refraction effects, especially at the ice bedrock interface. So that's why we need to include it. Yeah, I think it's important to have these in your heat flow estimates.
Sure. You talked to how the crustal architecture is really important in making a good heat flow map. And I wondered from your analysis of what's available in southern Australia, so you showed the beautiful seismic profiles that are available for southern parts of Australia. You know, do you have a feeling about the most important data sets that could be obtained in Antarctica to give you more certainty in your model?
Yes, so heat production values would be nice for actual validation of our results. It would be also nice to have a petrophysical database that also holds density and susceptibility values so that we can actually validate the relationship that we got. Yeah, for heat flow prediction, yeah, I think lithospheric models are very important to be constrained whether by seismic data, yeah, and sediment information. Yeah, I think, yeah, in terms of geology,
yeah,
this would be very important.
Okay, thank you. Laura, there's quite a few questions for you, but you're doing a good job of keeping on top of them in the Q&A. Some discussion about the relationship between the older ages you were discussing from the Prince Charles Mountains and Eastern Ghats and the Bunga Hills. Did you want to comment any further on that discussion?
I guess really I think we need some more isotopic data and things because they've been so reset in part by the granulite facies metamorphism. It's difficult to get an exact age peak, and that's the same problem in the Eastern Ghats. Is most of the geochronometers have tried to give up the ghost. So if we can get some isotopic data, at least we'll be able to compare an extra data set to try and work out the source region better.
Sure. Just monitoring the chat. I can't see any more in there. There's one open, but it's just a comment for you, Laura, that relates to another question. Any other questions from our attendees? I'm happy to pop you on the microphone if you'd like to speak, or pop it in the chat. I guess while we just spend another minute or so seeing if there's any other questions, I have a question for Dan. So you're looking at this early Earth history in the Napier complex. Is there other areas, example that Geoff spoke about earlier? Are there other areas of Antarctica that you're looking at to try and pull out this early Earth history?
Not at the moment, because I don't know of anywhere where anything older than about 3.4 has been seen.
Right.
The interesting thing is that's also the case in India, where the new data coming out with 3.4 and 3.5 crustal generation is being seen, but there's still nothing that matches the Eoarchean stuff in the Napier complex. It remains unique in this assembly. Certainly it extends under the Rainer, and there is reworking, as you know, in the Oi Gardens, and I'd like to have a bit more of a look in that part of reworked Napier that is the Rainer. But do you know of anything older than 3.3, Laura, that is in the PCMs? I don't think any of, we'd all love to see it, but we haven't been able to stick those two together.
Not really. I've got some discordant stuff, but it's not concordant, so it's pretty hard.
That's okay. Discordant doesn't mean meaningless.
Yeah.
I take what I can get.
Yeah, I'll have another look through my data.
I would be curious to know more and look into the Poles Together project is expanding in the next 3 years. We will be looking more at the Archean derivations of different things within East Antarctica, and I'd like to chat to all of you guys about that and where we might be able to go from here. That'd be great.
Cool.
Thanks, Dan. Well, if there's no other questions, I can't see any other ones coming through. Yeah, I'd just like to thank everyone across our 2 sessions for attending today, and all our presenters. It's not over, so there's still time to look at the posters, so please do check in there. And also, I understand this recording will be available within 48 hours on the SCAR website. If you missed some of the earlier talks, check in there. To any of our presenters who don't wish their talk to go onto the SCAR YouTube channel, please contact SCAR directly and ask them or tell them that, and so that your presentation would stay within the portal and not go outside, or you can get in contact with me too. I think Geoff has something to say.
Just want to thank you, Jackie, for all your effort. I mean, I've been a co-chair with you, but you've done a lot of work, so thanks a lot.
Oh, thanks, Geoff.
Yeah, I can second that. Jackie is certainly a champion in organising these sort of things, and I really appreciate all the work that she does, and it makes the rest of us look really good. And to be honest, it's mostly Jackie.
Thanks, everyone. Yeah, well, sorry we couldn't be in India again this time, but I said that 2 years ago that next time we'll be seeing each other. So maybe in another couple of years we can have a similar session in person. But do get in touch if you're interested in convening such a session. It doesn't need to be the 3 of us again. So, thanks everyone, and enjoy the rest of SCAR.
Thank you, Jackie. Well done.
Everyone.
Thanks, everyone.